1, 2. Yeah, yeah. Good. You're fine. Let's test again. 1, 2, 3. 1, 2. Ja, control off. Fine. Yo.
All right, if everyone could just take their seats, we'll be starting in a minute. All right, everybody, please take your seats. Welcome to the second day of Division G meeting. So a couple of reminders. If you are speaking, please, before your talk, so when the person before you starts talking, please go to the back and take a microphone so that you can be ready when your talk is about to start. Also, if you're online, please post any questions that you have on Slack. We'll be monitoring Slack for questions at the end of talks. Okay, so first I'd just like to invite up Andre Persha to discuss Division G days.
Good morning, everybody. Everybody can hear me all right? Perfect. So I have just a quick update for the schedule, if you don't mind putting that up. So we had 2 withdrawn talks, and we managed to find 2 sacrificial goats to fill those slots. Yep. So as you can see, session 3 remains unchanged. So that's this morning. Whereas session 4, if you don't mind putting us to the previous slide. So here, the 1:30 p.m. and the 2:30 p.m. have been withdrawn. So we now have 2 substitute talks. One by Steven Blumen, he'll be talking about black gem, and then I will take the second one talking about eclipsing binaries and artificial intelligence. So with that, that means that there will be no more gaps in the program. So if you are planning on joining us for that whole session, we will fill that session with science talks. All right, So with that, I will pass this to our current vice president and incoming president of Division G, Ms. Mariam Shadid.
So, good morning. Good morning, ladies and gentlemen. And I hope that you had a great weekend. And welcome to our second day of our Division G. I am sure that it will be once again very promises, inspiring day too. So first of all, let me introduce myself. So I am Miriam Shadid. I have had the privilege to serve our Division G as the vice president. So I'm originally from North Africa. I did all my my schools and the university in Casablanca in Morocco before moving to France and getting my PhD in Toulouse. In France. So I'm currently an astronomer at the University of Côte d'Azur in Nice. And I focus on stellar physics, of course, stellar evolution, structure, and pulsation by exploring ground-based observations in the heart of Antarctica at South Pole, and also space telescopes as well. So as an astrophysicist, I work on spectroscopic and photometric time series observations and instrumentation to challenge the shock waves phenomena and also atmosphere dynamics and pulsation modes, etc. So I am very excited to become president of Division G and really very happy working with you all. I'm sure that we will achieve a great success for our Division G. So as I'm stepping to my next new role as president, I would really to take this opportunity to thank our ongoing President Andre, for his incredible leadership and hard work, and also our past President David. Thank you very much for your work. And and all members of our steering committee Division G. And of course, I'm grateful to you all for your support and for being here. So thank you very much. I am sure that we have had a great thing for our Division G, and we achieve our goals. So I will do really my best to continue to make our division shine and achieve even more success for our division. So I will not be really very, so our division studies fascinating topics from binary stars and stellar evolution to massive stars and planetary atmosphere. And we are already a very large community. We are almost 3,800 members. And all of us, we are already committed to make outstanding results and discovery. So we will continue. We will continue to achieve our role for all stellar physics research and collaboration. And we will continue involved in the IAU symposia also. And I will do my best to improve communication. So one of my ideas is to create new newsletter of Division G. So we will start with quarterly newsletter to keep our members informing about any activities and opportunity for our Division G. And also, of course, social media to engage a very wider audience for our community G. And we will continue also to support a young researcher by giving them the opportunity to present their work, and also by awards, okay? And I have another idea is to host webinars, okay? For this to share our knowledge, and also for our really to share our knowledge and to discuss new development in astronomy and stellar physics. And we will also engage in education and outreach. So we will join the IAU office of education and outreach, and we will develop some research of schools, and also engage the member of Division G to involve in the outreach activities, and to raise our awareness of our discoveries, okay? And finally, I would also to discuss about stellar physics for sustainable development. So I'm committed to advance diversity, inclusion, and also open science for stellar physics to get sustainable astronomy or sustainable stellar physics. So there is some ideas, and I am still really flexible and open for any other suggestion that we can have together, and to achieve our goal toward our division success. So thank you very much for your support and for your trust, and let's doing together that, and let's moving forward together. Thank you very much.
All right, thank you so much, Miriam. Okay, so the next item on the agenda is that Andre is going to present the PhD prize.
Yeah, so before I go to that distinct pleasure, let me remind you that we have allocated 30 minutes at the end of today's day, so at 4:30 p.m., to engage in a discourse to try to figure out what Division G can do for you. So please, if you've not done so already, take a little bit of time to think over what Division G can do to facilitate the interaction between you and your colleagues. So if you have any suggestions whatsoever, we'd love to hear them, because this is how we go forward. We have had a similar event at the 2022 General Assembly and came with a lot of great ideas. So if you don't mind joining us in that session as well, so 4:30 p.m., we would love to hear all about it. All right, now let me invite Dr. Antoine Bédard. Please join me here. Everybody, please join me in a round of applause for our winner. Thank you very much. Good to meet you. Good to meet you. So Antoine is from Université de Montréal, n'est-ce pas? and he is our 2022 Division G winner. So I am presenting here the certificate.
Thank you very much.
Where you've won. I would like to again tell everybody that this is an extremely competitive award. So we've had a very large number of applications, and these PhD dissertations are truly outstanding. And so to choose an outstanding one among the outstanding ones, you can imagine, has been a very difficult process. And I hope that you will join me in congratulating Antoine for winning this. He has since been a postdoc, correct, at the University of Warwick?
Yes.
So he's already gone through, but please join me in congratulating him again.
Thank you very much. Thank you. Thank you very much. Okay, so hello everyone. First of all, I just want to say a big thank you to the steering committee for the award and for this amazing opportunity to be here in Cape Town and to present my research. I'm very grateful for that. And I'm also someone that tends to write very long papers. So I want to apologize to the committee that had to read the whole thing. Okay, so my thesis is about the evolution of white dwarfs, and more specifically about modeling the effect of chemical element transport on the evolution of white dwarfs. And I am going to talk about that topic today, but I'm not going to talk about my thesis per se. And I'm going to focus on a more recent work that I've been doing. And the reason is simply that I could not come to the stellar physics division day and not talk about these results. These results are pretty exciting, and I hope you'll share that excitement by the end of my talk. So I'm just gonna quickly go through okay, wait. So I'm gonna quickly go through the basics of white dwarfs. So white dwarfs are essentially dead stars. Over 95% of main sequence stars will end their lives as white dwarfs. Okay. They are extremely compact objects. They have about the mass of the sun, condensed within a radius similar to that of the Earth, and so they have extremely high densities. They have a pretty simple structure. So they have a large core made of carbon and oxygen, which contains about 99% of the mass of the star, and the core is surrounded by extremely thin layers of helium and hydrogen. White dwarfs have exhausted their nuclear fuel, so their evolution is a simple, continuous cooling process. So they start hot and bright, and they become cooler and fainter with time. And this is a very useful property, in particular for stellar age dating. So compared to main sequence stars, which barely change in billions of years, white dwarfs do change a lot. And so this is very useful to measure ages. And so white dwarfs are useful clocks to determine the ages of stellar populations. And I think this is probably the main reason why white dwarfs are interesting and important. And finally, one thing that's going to be important for my talk is that as they cool, the core of white dwarfs freezes into a solid state. And we call this process crystallization. And this is a nice artist impression of that process. And so that process starts at the center of the star. And as the star cools, the solid core grows from the inside out until the whole white dwarf is solidified. And here I just want to highlight that this is not a usual freezing process. So when that happens, the core of the white dwarf is 10 million degrees. But yet the density is so high, the ions are so closely packed together that the plasma turns into a solid. So that in itself is very interesting, I think, because those are extreme physical conditions. Now, like all fields of stellar astronomy and astrophysics, Gaia has revolutionized the study of white dwarfs. So Gaia multiplied the number of known white dwarfs by a factor of 10 and the number of parallaxes by 1,000. So basically Gaia gave us the first detailed HR diagram of white dwarfs, which is shown here on the right. And so the distribution of points in this diagram is pretty much what we expected. White dwarfs cool with time, so they evolve from the top left to the bottom right. And so this is simply an evolutionary sequence. But there were a few surprises, and in particular, I think the most unexpected feature is this feature here, this kind of overdensity here, which has been called the Q branch. And so the purpose of my talk is to explain what is weird and about this feature and why it appears. So this is the same HR diagram, but with cooling tracks shown in blue for various white dwarf masses. So as you probably know, white dwarfs have a peculiar mass-radius relation where more massive white dwarfs have a smaller radius, and so they are fainter. So this is why more massive tracks are below the less massive tracks. And so this, first of all, tells us that the Q branch, which is delimited by those orange lines here, is composed of massive white dwarfs. And what's odd about the Q branch is that it's transverse to the cooling sequences. So that tells us that, well, the only possible interpretation is that some high mass white dwarfs initially cool normally, and then when they get here, they experience a cooling delay, so they pile up at this location. And one thing that's very interesting is that those orange lines here are not any lines. They delimit the region where we expect the core of white dwarfs to crystallize. So there's really some interesting physics going on here. And we can get more information about the cooling delay by looking at the kinematics. So this is the same similar HR diagram, but with a third dimension added here, which is the transverse velocity. And I won't go into details about that because of the time constraints, but because the kinematics is an independent age indicator, we can use the kinematic information to figure out exactly what fraction of white dwarfs are delayed and what is the length of the cooling delay. And they did this in this paper, and they found this amazing result that a small fraction of high mass white dwarfs completely stop cooling on the Q branch for at least 8 gigayear. And so this is really remarkable because what kind of energy source could stop the cooling of white dwarfs for 8 billion years? So I think this is probably one of the most intriguing stellar physics questions I've come across in my short career. Because, well, white dwarf cooling is supposed to be very simple, very well understood, but clearly these objects have a very powerful energy source that we knew nothing about. So how can we be that wrong? And so so a lot of people started working on trying to identify what is this energy source. And most people agreed that the answer had something to do with neon-22. So why neon-22? The core of a white dwarf is essentially carbon and oxygen, as I mentioned, but there are also some trace elements, and the most abundant of them is neon-22. It's simply a product of core helium burning, and the abundance of neon-22 is approximately equal to the metallicity of the progenitor. So for normal, typical solar metallicity stars, this is typically 1 or 2%. And what's special about neon-22 is that it's a neutron-rich isotope. It has more neutrons than protons, and so it is heavy. It is heavy compared to the carbon-oxygen background. And this means that when it is transported downward into the white dwarf, it releases gravitational energy. And you can do a quick back-of-the-envelope calculation, and you would find that if you were to take all of the neon-22, which is distributed in the white dwarf core, and concentrate it at the center, you would get approximately enough energy to explain a very long cooling delay. And so the question becomes, what is the physical mechanism that transports neon-22 to the center of the white dwarf? And so there's been a lot of research on this. So I'm not going to, obviously, I'm not going to go through that all. I'm just going to focus on what turned out to be the solution. So a collaborator of mine, Simon Bloin, a few years ago, suggested that the crystallization of the core can trigger what he called a distillation process that would concentrate all the neon 22 to the center. So I'm going to explain briefly what I mean by distillation. So when crystallization occurs, it causes what we call chemical phase separation. This simply means that the solid crystals have a different composition than the liquid, and so they have a different density. And this is something that we can calculate from first principles. If we know the composition of the liquid, we can predict what is going to be the composition of the solid. And for typical neon 22 abundances, we find that the solid crystals are heavier than the liquid, so they are stable. And this is why we get this standard crystallization scenario where a solid core simply grows from the inside out. But then some white dwarfs are not formed by single star evolution. They are formed by mergers, and some types of mergers can enhance the amount of neon 22 in the core. And if we do the same calculation for an enhanced abundance of neon 22, we find a completely different picture. So what happens is that if the neon 22 abundance is over average, the crystals are actually depleted in neon 22, which means that they are lighter than the liquid. And so what happens is they float and eventually melt, and this is illustrated here. And if the light neon poor crystals float, this means that the heavier neon-rich liquid sinks and is displaced downward. And this is a continuous process that can very efficiently concentrate all the neon 22 close to the center. And so this was a very promising suggestion for the energy source. But then the next step was to answer the question where, can neon 22 distillation explain the Q branch? And so that is a project that I've been doing with Simon and other people. And so we published those results earlier this year in Nature. So you can kind of guess that the answer is yes. So the first step was, to answer the question, what is the effect of this transport process on the evolution of white dwarfs? And this is exactly my field of expertise. So I was kind of at the right place at the right time with the right expertise to answer the question of the hour. And so I'm going to just show a few slides to summarize this. So this plot here shows the neon 22 abundance profile inside the white dwarf at different phases. So the dotted line is the initial distribution. So
You've got 3 minutes left.
Okay, perfect. The neon 22 abundance is pretty much uniform, but then the dashed and solid lines show what happens as the distillation process unfolds. And so the neon 22 gets concentrated in the inner 25% of the white dwarf. And this releases a lot of gravitational energy. And so the effect on the cooling is drastic. So this is shown here on the right, surface luminosity as a function of time. For 3 different white dwarf masses, the dashed lines are cooling sequences without distillation. So this is the normal behavior. Luminosity simply decreases with time. And the solid lines show what happens when you include the distillation process and the energy release. And so the luminosity and temperature remain constant for between 8 and 12 gigayears. And so this is really remarkable because this is essentially the behavior of a main sequence star. So this is the second life that I refer to in my title. This is a really remarkable result. And then the next question was, can we reproduce the Gaia data with these new models? So we did population simulations. We focused on this mass range here, the most massive white dwarfs. Here is a simulation with standard cooling models, so no distillation, and this kind of shows that, well, since white dwarfs cool continuously, they don't pile up anywhere. And then if we add a small fraction of white dwarfs that experience the distillation process, well, some white dwarfs initially cool normally, but then they get stuck here because their cooling is stopped by the energy release. So they pile up at this location. And if we overlay the data, we get a very good agreement. So, and we can make a more quantitative comparison, which is shown here. So this is the histogram of this zeta parameter, which is defined here on the left panel. So it is defined such that lines of constant zeta are roughly parallel to the Q branch. The data here are shown in black. So the Q branch is this very nice sharp peak. The blue line is a simulation without the distillation process. So we have no peak whatsoever. And the red line shows simulations with the distillation process. So we can reproduce very well the location, the width, and the amplitude of the Q branch. So the conclusion, well, it's all in the title. Some white dwarfs have undergo a distillation process where they form crystals that float and displace heavy neutron-rich isotopes to the center. This provides a very powerful source of energy that interrupts their cooling for billions of years. Thank you.
Thank you very much. Can I just remind the next speaker to make sure that you go up and get the microphone before the start of the talk? So at the start of the talk, before your talk, go to the back, please. Okay, so do we have any questions? Dave here.
This is really great, Antoine.
Thank you.
I'm going to throw a left field ball at you, maybe, I don't know, but what's the effect of magnetism?
We actually had that question in one of our referee reports, so that's a good question. I think the answer is that magnetism cannot have such a huge effect because well, you can make a quick calculation of what magnetic field you would need to alter the structure and evolution of a white dwarf, and you get something like 10,000 megagauss. 10,000 megagauss, and the most magnetic white dwarf that we know is like 900 megagauss. So even the most magnetic white dwarfs known couldn't be affected. Yeah, the magnetic field has no influence on the structure and evolution.
Thanks.
Yeah.
Thank you. This is beautiful. Jan Christensen, Dalsgaard Robus. I wonder, for this to work, you need about 7% of the white dwarfs having this overabundance of neon. How does that compare with estimates of how many white dwarfs you produce in the galaxy through merger processes?
So yeah, that's a very good question. And so the answer is tricky. So not all mergers are expected to enhance the neon-22 abundance. So not all merger products are expected to stop cooling like this. So there's still work being done to identify which kinds of mergers can give this overabundance of neon-22. And one merger channel that has been identified is the merger of white dwarfs and subgiant stars. And the merger rate of this kind of mergers matches roughly with 7% of all ultramassive white dwarfs being delayed. So yeah, but there may be other channels that we don't know of yet.
We have time for another question right at the back.
Thank you for your talk. Okay, I just want to know whether, do you consider the white dwarf that is in the binary systems?
You mean in the population simulation?
I mean, the white dwarf that is in the binary system, is there any effect of the thing that you do?
No, not really, especially for those high masses. So So high mass white dwarfs are either single stars or the product of mergers. So not a lot are in binaries. So I don't think that would have a large effect.
Thank you.
Any more questions? Oh, just here. Oh. Okay, the one at the back first.
Hi, thanks for the really interesting talk. This isn't exactly my field, so this is likely a stupid question. Could we expect this distillation process to happen in other types of stars or stellar objects?
Well, one thing that's sure is that you need a core forming solid crystal. So we wouldn't not expect this on the main sequence, for example. Maybe in neutron stars, I don't know. I have no idea. Yeah, so the important ingredient here for the distillation process to happen is the overabundance in a neutron-rich isotope. So this means that we could expect to see that in white dwarfs that are produced by single star evolution, but from a high metallicity progenitor, for example.
Okay, thank you so much again.
Thank you.
All right, and next up we have Lee Townsend. You have 7 and 3.
Great, thanks. Hi, everyone. Can everyone hear me okay? So my name is Lee Townsend. I work right here in Cape Town as a salt astronomer at the South African Astronomical Observatory. And in the next 5 minutes or so, I'm going to tell you a little bit about our ongoing project on SALT to monitor BE X-ray binaries. So very, very briefly, BE X-ray binaries consist of obviously a very massive B or O-type star with a compact object, which is almost always a neutron star. So given this is a talk about SALT, the optical characteristics of these systems, underlying blue spectrum with prominent hydrogen lines. But the BE nature of these stars means that we see, in the SED, we see infrared excess. We also see Balmer lines in emission, in strong emission. We often see helium and other lines such as iron in emission. And all of these features come from this decretion disk around the BE star. And this is produced through some combination of rapid rotation and non-radial pulsations within the star. So the disk itself is much cooler than the photosphere, which is why we see this infrared excess. But the disk itself also shows variability on many timescales. And I'm talking about X-ray binaries specifically, but this variability we see and a lot of the optical features are generic for all types of BE star. So the graph you can see here shows this kind of, this is around 10 years along the x-axis. This is an ogre-like curve showing very long-term changes. And this is indicative of the BE disk growing and shrinking. The plot on the right shows variability on much different timescale. You can see there's very little long-term variability, but we see this periodic flaring. And this is caused by the neutron star at periastron going through the disk, interacting and kind of churning up the disk a little bit. So why do we study BE X-ray binaries specifically? And there are many good reasons. They're very important for massive stellar and binary evolution. The physics of accretion onto neutron stars, accretion physics, physics in highly magnetized environments. And see, these are some of the highest magnetic field neutron stars we know of. They're also recently been shown to be sources of ultraluminous X-rays. And there are examples of 2 or 3 of these systems, famously one in the galaxy a couple of years ago, that have gone into the ultraluminous regime. And of course, they're very likely to be prominent formation pathways of double compact object binaries. So a couple of slides very briefly on SALT. As I said, I work for SALT. So SALT is in Sutherland, which is about 400 kilometers northeast of Cape Town. The site itself is very good for diffuse faint object science. So it's very dark skies. We also have a modest seeing of around 1.4 arcseconds median. So I don't have time to talk about SALT too much. I would encourage all of you to go to the SALT and the SAAO booths in the exhibition hall. But a very brief summary of the instrumentation we have. We have three main spectrographs now. RSS, which is our kind of workhorse spectrograph, low to mid resolution, with a full optical coverage down to about 350 nanometers. This has a lot of different modes: polarimetry, multi-object spectroscopy, and we have recently commissioned an IFU. Then we have a high-resolution spectrograph with resolving powers of about 15 to 65,000. And we are soon to have an LFC. We're commissioning this now, which should allow this instrument to get down to about meter per second precision. Also recently commissioned is a near-infrared spectrograph, which is an IFU, again with modest resolving power, covering down to about H-band. So if you think you can use these instruments for any of your science, then please chat to me or come to our booth. So a summary of our project. So the title said 10 years of optical monitoring. It's actually closer to 13 years now. Started in about 2011 with regular observing from 2013. And in our sample, we currently have about 1,400 spectra taken over this 11 or 12-year period, most with RSS, but now also quite a few with HRS. And what we want to do with this program is really have one of the largest spectroscopic databases for this type of system. And again, it's not only useful for BE X-ray binaries, which is the type of science I'm interested in, but I think more broadly, the BE star community. We're monitoring systems mostly in the Milky Way, about 18 objects, but also several in the SMC. And as I said, many of these objects in our data set now have at least 25 to 30 epochs, some 50, some even 80. And so this is really good cadence, good resolution, good signal to noise spectroscopy of a large fraction of these systems. And this is an example spectrum from HRS, just so you can see the kind of science we can get. We can see here's the H alpha line, very prominent V over R ratio. We can see a different velocity profile between the blue and red peaks. And also there's this substructure in the blue shifted peak as well. So it's really telling us a lot about what's going on in the BE star disk. And a lot of this variability is caused by the interaction with the neutron star. So my last slide, what do we want to do with this data set? And this is a work in progress. So we want to do a population study of how the Balmer lines vary. And I think I forgot to say this, but the Balmer lines are a very good proxy for what the disk is doing. And so you can see this example on the right. On the top panel, we have the H alpha equivalent width against the long-term X-ray light curve on the lower panel. And you can see this is a very kind of easy to understand case. The disk grows and we see some X-ray activity. The disk shrinks away and the X-ray activity fades. But what we can now do with our data set is doing this not just for 1 or 2 systems, but for 40 or 50, 60 systems. So we're going to get a really good idea of how the disk behaves and interacts with the neutron star and how this affects the X-ray activity we see. Okay, so I'm out of time now, so I'll leave you with my summary. Again, we have almost 1,400 spectra in our catalog at the moment. This is an ongoing project, and we obviously want to do a lot of science with this, but eventually we will be releasing this as a catalog for the community, as a community resource, and hopefully integrated into existing X-ray monitoring tools, specifically at ESA, and incorporating this into ESA Sky as well. So thank you.
Thank you very much for an interesting talk. Okay, any questions? Sure.
Thank you very much for your talk, a very good talk. So I have just a question about the radial velocity. So do you know about which exactly precision in the radial velocity
Of
curves?
the HRS.
Oui, in high resolution spectroscopy.
Yeah.
Thank
So at the moment we're at the level of kind of tens of meters per second precision, but we are commissioning a laser frequency comb, and so this should bring our radial velocity precision right down, maybe even to sub-meter per second. But there's a talk, I actually forget which session, but Lisa Krause, who's one of our observatory scientists, she'll be talking specifically about the LFC and high resolution capabilities. Sure.
Any other questions? At the back there.
Very nice talk. How have you selected the sources that you're monitoring? And in particular, is there any correlation with the neutron star properties that you made you choose the ones that you chose?
Yeah, actually, it's more related to the optical magnitude. So when the project began back in 2013 or so, we were monitoring the most X-ray brights, obviously, because that's the thing that made sense. But as the project developed and we got more time on SALT, we expanded that to include a good fraction of the SMC population, which is something we wanted to focus on. But when we started observing more with HRS, we focused on the optically bright systems in the Milky Way. So the 13 or so systems we're monitoring with HRS are the very bright Milky Way systems. And this is because we wanted as good signal to noise as possible, because we're planning to do a radial velocity study of these objects, hopefully to include significantly enhance the binary parameter space of some of these systems.
Okay, I have one last question.
Sure.
Do you see any evidence for inspiraling from the companion stars?
You mean orbital?
Mhm.
No, we don't.
There
is some evidence on some supergiant systems, but I think BE X-ray binary specifically, no.
All right, thank you so much.
Thanks.
Let's thank the speaker again. And the next speaker is Kushik Sen, talking about massive algals. You have 7 + 3.
Hi everyone, I'm Kaushik, and I want to thank the organizers for giving me the opportunity to talk about some observable properties of massive algals. And if you haven't woken up already, these are some pictures of nice penguins. This is what I was up to on the weekend. And to follow this up, I have a question. What is the relation between Batman and eclipsing binaries? So thousands of years ago, ancient astronomers, when they looked up into the night sky, they saw that their idea of a static heaven was changing. There were some heavenly objects which were changing in brightness. And they got scared and they called them algols, or the heads of the demons. Now, the word algol was derived from the word algol. And that is why these eclipsing binaries were the first algols to be discovered. So this is the connection between algol and algols. So now, of course, fast forward thousands of years, algol is a star system that shows periodic variations in brightness. And if you look at the parameters, the less massive star is more evolved than its companion. So this is the typical algol paradox. And the way to solve it is understanding that these are actually mass transferring binaries, and so on. So there is a lot of theoretical and observational work done on algols, but I would say that the literature is IMF weighted. What I mean is that most of the work has been done on the low and intermediate algol binaries, but the massive algols have received a lot less love over the last 2 centuries. Now, a brief introduction on how to form these algol systems. You take two massive stars. I am talking about massive algols, so I'll take massive stars, put them in a short orbit, find out the equipotential surfaces, then take the Roche lobe of the two stars and evolve the binary. So as the binary evolves, the more massive star will increase in radii faster. There will be a Roche lobe overflow, and then there will be a thermal timescale stripping of the donor star's envelope, and you end up with a less massive donor, which is stripped of its outer envelope, transferring mass to a more massive companion. And this mass transfer happens at the nuclear timescale expansion of the radius of the donor because the binary orbit is widening. And this is why we see this phase as the algol binaries. Now, the question I want to ask today is the configuration of algol same for all masses? So is the donor always the less massive star? Now, to answer this, the first idea is that the ratio of the core mass to envelope mass in massive stars, as you go up in mass, it keeps on increasing. So if you have a sufficiently massive donor with a lower mass companion, it may happen that you can strip the envelope of the donor and still the donor remains the more massive component of the system. And to show this, I calculate a model with a 45 solar mass donor with a mass ratio of 0.5 in an orbital period of 8 days. And this is the Kippenham diagram of the donor. So this is the total mass, and you see that the mass decreases quite fast. This is the fast thermal timescale mass transfer. And then there is this nuclear timescale evolution. Now, if you put the mass of the accretor here, which is shown by this dashed line, if the mass transfer efficiency is sufficiently low, then you can have this nuclear timescale mass transfer where the donor remains the more massive component of the system. So in the 10 to 40 solar mass range, most of the algols that you see will have a mass ratio inversion. This is the typical result we know for centuries, that the mass ratio gets inverted. But if you go to higher masses, say from 40 to 90 solar masses, you get a significant fraction of semi-detached binaries where the mass ratio does not invert. So the donor remains the more massive star of the system. And we found, so while these are the ordinary algols that we know, we found two systems out of 5 semi-detached binaries in the VFTS TMBN survey, where the donor is more massive. And these are what we call the reverse algols. Now, how does this evolution look on the HR diagram? So this is the same donor star and the accretor. The red one is shows the evolution of the donor on the main sequence. The blue shows the evolution of the accretor. Now, before the fast thermal timescale mass transfer, the donor evolves like a typical O star. But after the mass transfer, you strip a lot of mass. So the L over M ratio increases. So a higher L over M ratio means a higher mass loss rate. A higher mass loss rate means that you can have optically thick winds. And these stripped donors can show emission lines in the spectrum while they are on the main sequence. And the observable counterparts would be the hydrogen-rich Wolfride binaries on the main sequence itself. And to quantify this, what we did is we calculated a wind optical depth parameter where everything on the right-hand side are measurable for observed Wolfride stars. And also we can derive this quantity for our donor model. What we find is that if you calculate this tau for all observed hydrogen-rich Wolfride stars on the main sequence, you find that the tau is greater than about 0.1 for the LMC observed stars. So then we compare this with the evolution of this optical depth parameter for our donor model on the main sequence. So this jump is the fast case A, and before the mass transfer, the optical depth parameter is very low. So they behave like an ordinary O star. But after this thermal timescale mass transfer, the optical depth parameter has an order of magnitude jump, and the parameter is in the right ballpark as the observed OF or OF/WN or WN stars. So this gives us gives a verification that these strip donors can be observable as Wolf-Rayet stars. Now, if you are already not convinced that massive algols are really interesting objects and we should study more algols at the massive end, here's a cartoon of the formation channel of gravitational wave progenitors. And there are, of course, a lot of uncertainties. But since algol has this nuclear timescale mass transfer phase, which comes just after the thermal timescale mass transfer, you can derive empirical constraints on mass transfer efficiency. Then these are short orbital period systems. So you can study the strength of tides through circularization, rotational synchronization of these donors. And finally, these also have stronger mass loss rates, as I said. So they can be also important for chemical enrichment of the interstellar medium. And I leave you with my takeaway messages, and thank you for your attention.
Thank you so much. All right, do we have any questions at the back there?
Hi, Kaushik, very nice talk. I was wondering, since you talked about Wolf-Rayet stars as the potential massive algol donors, did you compare to the observed LMC populations if the Wolf-Rayet population there makes sense? And for example, for the binaries, if they have the companions that you would expect from your scenario?
Yeah, we did one detailed comparison with BAT 19113, where we found a Wolf-Rayet, where there is a Wolf-Rayet star of 52 solar masses and an O star of about 30 solar masses. So the mass ratio checks out because the Wolf-Rayet star is more massive. And also we compared the L/M of the Wolf-Rayet star and found that if you use single star tracks, then the L/M ratio is too low for that luminosity and temperature. But if we have a binary strip star from our models at the same luminosity, then you can explain the L/M ratio much better.
All right. One last question. Thanks.
Hi, and really nice talk. So you mentioned also two VFTS objects that you found correspond to this scenario. So I'm going to ask a similar question. Did you look at their L2M and do they show Wolf-Rayet-like features or enhanced winds of any sort?
No, I did not compare the VFTS systems. One of the reasons is because they are a bit less massive. So all the reverse algols that we have in our models do not also go through the Wolf-Rayet phase on the main sequence. So there is also a mass dependence. So I did not check the L/M of those reverse algols. So those are semi-detached systems as well.
All right, thank you, Kaushik. All right, so the next speaker is actually online and they have posted a video. And so we'll be watching the video of Lucian Wang.
Good morning, everyone. I'm Lucian Wang. I'm a postdoc from the International Astronomical Observatories. I'm sorry I couldn't be there in person to participate in this conference, but I'm excited to share our recent studies on detecting and characterizing astute companions of massive stars. And first of all, I want to thank all my collaborators, including Professor Douglas Geis from Georgia State University, USA, Professor Geraldine Peters from Southern California University, USA, and Dr. Robert Clement from ISO in Chile, and Professor Zhang Wenhan from Yunnan Astronomical Observatories, CAS, China. Multiplicity is common in stars, and for stars spans from all different spectrum types, the fraction of a multiplicity increase towards massive stars. So such a result suggests that for massive stars, and they will somehow interact with their companions during the course of their lifetime. And among the massive stars, there is a special category of stellar population known as BE stars, and they are featured by their reputation and also the presence of circumstellar depletion disk around the star. And the BE stars are observed in many of the BE binaries with different companion features. And the theoretical calculations using the binary population synthesis model suggest that for BE binaries with a low mass companion, such as a hot SD over SDB subdwarf companion and a white dwarf companions, they should be very abundant near Milky Way. But however, observationally, we only found a few so far. And for the to the high mass end for the BE binaries with a neutron star companion, and Professor Townsend just explained their features in the earlier talk today. And so far, observationally, we haven't found any further evidence for BE binaries with a black hole companion so far. So why BE binaries are important? Because such binaries, they occupied at a critical evolutionary stage for massive stars. So during the early evolution, through binary interactions, the former mass donor star stripped off its outer atmosphere and left with a very tiny, hot, and liquid helium core stars, and then to form a non-degenerate BSD over SDB binaries. But however, depends on the mass of the companion stars. Such binaries eventually they could be involved to like a supernova event and then to become a high energetic BX3 binary events. So these binaries they might be even linked to all the exotic binary events. So how do we detect the STU companions of BE stars? And we have been using multi-wavelength approach to search for the signature of the STU stars and then to carry out follow-up studies to investigate their properties. So these include the FUV spectroscopy using the space observations, such as the IUE and also the HST. And for ground observations, and we use the APO for northern targets, and using the CTIO, the Smart Telescope, for the southern targets. And in addition, we also use the optical and the near-infrared interferometric observations from the long baseline Chara array and also the VLTI to map their orbit. So let's talk about the FUV spectroscopy first. So because the S2 stars is much hotter compared to its primary BE stars, so the basic idea is that we construct a model template spectrum for the S2 star, and then we cross-correlate the model template with our observations to search for the possible signature of the S2 star. And once we reach to any candidate detections for the S2 stars, we will be using the HST as a follow-up to confirm the detection of the S2 star. So showing on the right panel is one spectrum plot of the confirmed BE-STO binary from HST. And the observed spectrum is shown in the black color. And then the blue color is the spectrum for the BE component. And then the spectrum for the S2 stars is shown in green color. So as you can see, our observed spectrum is pretty much dominant by the BE stars. So the S2 stars actually contributes a small fraction of the flux to the observed spectrum. So the observed cross-correlation functions of the binary systems actually contains a composite feature for both two components, including a very broad contribution from the replicating BE stars, showing as the red color in the left panel. So by subtracting the contribution from the BE component, what will be left over will be the residual feature for the S2 star only, which is shown in the green color in the left panel. And then based on the morphology of the residual signals, then we are able to derive their atmospheric properties, such as based on the peak strength and the peak height, we're able to derive their flux ratio and their temperatures. And then based on the width of the residual feature, we're able to derive the VISA I values of the S2 stars. And in addition to that, based on the location of the residual peak, we'll also be able to measure the radial velocity of the STO star. And we also carried out a 3 to 5 year ground observing runs to complement FUV spectroscopy. So by measuring the radial velocity of the primary BE stars from the very broad H-alpha profiles, then we are able to plan orbital fits to determine their orbital parameters. And in addition to that, so based on observations from interferometric observations, and then based on the results from the spectroscopies, then we are able to construct the 3D orbits for the BE binaries. And then use a distance from Gaia, then we are able to derive the absolute dynamical masses for component stars of these BE binaries. So eventually, so what can we get from all these multi-wavelength observations? So we are trying to determine the intrinsic fundamental parameters of the BE and STO binaries, including their physical, their atmospheric, and also their orbital parameters. Because for all the parameters we measure so far, and they are not consistent with the ones from model prediction. So we hope these measurements will benchmark models to constrain important binary interaction process to answer some of the questions, such as what is the dynamical stability of the binary system? And during the mass transfer, how much mass actually was transferred from the donor star to the gainer star? And then what would be the accretion rate of the gainer star during the process? And then also during the mass stripping process, what is the mass transfer efficiency of these binary systems? Yeah, that's all my, that's what I have. Thank you very much for your time. And I would be more than happy to take any questions if you have.
All right, do we have any questions? I'm not sure if the speaker is available.
Yes.
Oh, you're here. Okay. Okay. Just over here, please. Oh.
Thank you. Very exciting. This is Andre Prussia. Can you tell us what is the minimal resolving power of the spectra that you need to detect an SDO as a companion?
You mean for the optical range or in the far UV
Yes.
range?
Well,
Yeah,
either
in optical range. Sorry?
the optical is what I meant.
Yeah, optical range actually is, we normally will search for the signature for the STO stars from indirect evidence, such as the helium-2, 4686 nice. So for other night profiles, it's almost impossible to see that. So that's the reason why we have to preferentially to search for the features in the far UV. So for the optical range, I will say more than 50K, the resolution probably will be enough to measure the radial velocity in a very precision level.
Makes sense. Thank you.
Yeah, thanks.
All right, one last question at the back.
Very nice talk. I was interested in the mass range of that you derived from your observations up to 1.7. Given the originally high mass of these stars, wouldn't you have expected to find that go to higher masses, or is this an observational selection of some kind?
Do you mean the mass of the STO star?
Yeah. Yes.
Yeah, so normally in our sample, what do we have so far? The mass is around 1 solar mass. So occasionally go beyond 1.4 solar mass. So as you mentioned, yes, during the searches, we did have some selection effect and bias because the STO star is actually too faint. So we can only find relatively bright ones in the far UV. But especially towards late type B and B type stars, we don't have any subdwarf detection so far for the late type B stars. So as I mentioned before, yes, the selection effect might be one of the reasons.
Okay, thank you.
Thanks.
All right, thank you so much. So the next speaker is Zlot Kesali. Are they here or maybe online?
Yes, hello everyone. Can you hear me fine?
We can hear you. And okay, your slides are up. So you have 7 + 3.
Perfect, thank you. So welcome everyone. My name is Jolt, and I'm currently a postdoc in Japan. And in this presentation, I would like to talk about the most massive stars that we know of. And this work is in collaboration with Joe Puls, Alex Decoder, Norbert Langer, and Sara Brands. And in particular, Sara performed a spectroscopic investigation of stars in the R136 cluster. So we aim to use our evolutionary models to match the observed properties of those stars. And they're located in the 30 Doradus region of the Large Magellanic Cloud, which is a quite complex star-forming region. And if we zoom into the center of this site, then we see the R136 cluster. So in this presentation, I will only try to focus on those stars whose masses exceed 100 solar masses. And so they are located in the core of this cluster. And in order to compute evolutionary models for these really massive stars, the most important physical constraint and input are the mass loss rates. So our strategy is to use a combination of what we deem to be optically thin and optically thick winds. Of course, this is a large oversimplification. In evolutionary models, we don't have optically thin and thick winds, but we are using the surface composition to switch between less efficient and more efficient winds. This is how our standard grid looks like from 200 to 800 solar masses. And what you see very clearly is that the mass loss rates are, of course, very high, but they become particularly high before turning to what I call the downstream evolution. So in this middle evolutionary path, the models with various initial masses join and produce helium-rich stars. The inset over here shows a typical model, and the surface is completely dominated by helium. So these stars, because of their very strong mass loss and because of the nearly linear mass-luminosity relation, are actually able to decrease their luminosities very, very significantly on the main sequence. And in this presentation, I will also argue that at least 2 out of these 3 very massive stars, A2 and A3, are possibly in this downstream evolutionary channel. It's also important to point out that the initially most massive progenitor is not the most massive in the pre-supernova stages. And actually this difference, this mass turnover, is already established on the main sequence. So the 800 solar mass model becomes nearly 40 solar masses at the terminal age main sequence, and then this difference is maintained until the end of carbon core burning. So it's important that there is no linear relation between black hole masses or final masses and initial masses. So here it is in some more detail. From 100 to 800 solar masses, the masses are shown as a function of time. And optically thin winds characterize the early evolution. Once the surface becomes helium-rich, we switch over to stronger, more efficient mass loss rates that we assume to represent optically thick winds. And so that's when the trajectory becomes much steeper. And at some point in the evolution, it becomes a degenerate problem to say what the initial mass was. And as I pointed out before, the most massive supernova progenitor will originate from somewhere around 160 solar mass progenitor. But what's also interesting here is that if we look at the time when the first supernova could take place at about 2.67 million years, then if all these models were hypothetically present in a cluster, then the most massive star that could be observed at that time would only have 74 solar masses. So if we're looking at a cluster that has evolved beyond 2.5 mega years, then we don't really expect to see very massive stars. They will look like massive helium stars instead. And it's interesting also to consider what their final properties can be. And this figure here shows the carbon-oxygen core mass as a function of the initial mass. So our standard grid is shown with the magenta. And in that case, we don't predict pair instability or pulsational pair instability at the Large Magellanic Cloud. Also, we don't predict a linear relationship between the final mass, final core mass, and the initial mass. Now, these results are extremely sensitive to the mass loss rates that are considered. So if we change them by a factor of 2, or if we switch to a different Wolf-Rayet type mass loss prescription, then the results can actually enter into the pair instability regime. When comparing our models with observations, it's actually important that we don't just place these stars on the HR diagram, but we actually consider as many spectroscopic observational parameters as possible. So here is one example for the, thank you, for the case of the surface helium abundance. And the observations here are from the Bruns et al. Study with lower and upper limits. And we see that at least for the 2 stars, A2 and A3, their surface helium abundance is quite high. So previous inferences assume that because they lie on this track with about 250 solar masses, that could be their initial mass. But if we actually make an interpolation between these models and split them to 2 parts, hydrogen-rich on the left and helium-rich on the right, it's quite clear that at least these 2 stars are not compatible with the red word for horizontal evolution in the HR diagram. Instead, we argue that they actually could originate from any progenitor in the mass range from 250 up to several hundreds of solar masses. We cannot rule out the possibility that the progenitor was maybe a 500 or 600 solar mass star. So I will conclude here that we are focusing on the most massive stars, and we argue that possibly previous inferences could underpredict their masses. They could have been much more massive. If mass loss is very efficient, they will lose mass very quickly and become helium-rich stars by the end of the main sequence. We are also predicting a lack of pair instability events at the LMC from these progenitors. So possibly the final outcome, the supernova events, could be rather typical or normal in this case. However, these results are extremely sensitive for the adopted mass loss rates, which we aim to best calibrate and best match, but we actually would need to go even to higher precision to have more firm predictions. Thank you very much.
Thank you. Okay, do we have any questions? In the back.
Hey Zolt, it's Tomer. Really nice work. I wanted to ask you if you think that if the progenitors were indeed, let's say, 500 or 600 solar masses, they must have lost 400 solar masses or so in the past few hundreds of thousands of years. Do you think that could have observational counterparts? The ISM, ejecta, stuff like that?
Yeah, hi Tomer, thanks for the question. So the difficulty is that the few hundred solar masses that these progenitors could lose would actually take probably about 1.5 million years. So if their present masses are of the order of 200, 300 solar masses, and if the progenitor was much more massive, then there's actually ample time to diffuse that material in the ISM. So one possibility could be that there is a kind of bubble around the cluster that partially contains this material that was removed from these stars. But it's very difficult because the timescales are quite long, actually.
Okay, thank you. Next question.
Me? Okay, thank you. Very interesting. So what about other stars in the cluster? Have you studied other stars in the cluster? Are they equally massive? Or why is it that those central stars are the most massive ones?
So probably, yeah, let me answer this in 2 parts. We have looked into some of the other stars, and we can also match them with our models. But it seems like that the 3 stars that are particularly massive, with present-day masses of about 200 or 300 solar masses, it might have to do with their formation. So the site of R136 and 30 Doradus is maybe a filament-filament collision that creates those really strong overdensities that are required to form these stars. Having said that, it's actually really difficult to say how these stars formed. It's a challenge for current star formation models.
We also have a
Okay,
question online.
Yeah, so sorry, one last question, and then I refer the speaker to the question online afterwards. I'm afraid we don't have time for that right now. So, Jeff.
Hi, nice talk. I was wondering if you considered close binary evolution in your modeling, because that will speed things up quite a bit, especially when they pass through a certain part of the HR diagram that I call the RQ diagram.
Yeah, that's an excellent point. So actually, as far as we know, these stars are not in binary systems. In fact, Tomer, who was just speaking earlier, has a recent paper that shows that there is possibly no companion stars for these three most massive. So we believe that they are genuine single stars, and they could have, in principle, formed by stellar mergers. That's a possibility.
Right.
But we actually think that's not the case, because if we look at the helium abundances as a function of time, it has to be in the single star channel at least. It has to be produced in the stellar core. So in order to bring that to the surface, a certain time has to pass. But if there is a merger scenario, then the initial masses are less. And actually the time to produce that helium overabundance is more. So it's quite a challenge to explain the nature of these stars with binary models, I believe.
Yes, but the lower mass stars, instead of just the top three, if you consider a run-of-the-mill 200 solar mass star, 100 solar mass star, they could be close binaries, and that probably hasn't been investigated too much. I'd suggest looking for anomalous outflow and possibly even asymmetric outflow with some period, to investigate that problem. But excellent work.
Thank you.
All right, let's thank Joel again. Thank you. And the last speaker is Atsuko Nita.
Thank you.
You have 7+3.
Okay. I work at Gemini Observatory, and I brought some stickers and brochures and macadamia nut, and I didn't know that the room was going to be this big, but I was just going to pass it. So if you can just take it and pass it around. Okay. Hold on. This is okay. All right. So I'm going to talk about the white dwarf stars. We had a wonderful talk at the start of this session to say why we study white dwarf stars. I know from my work being a middle manager that I have to tell kids 7 times before they get it, and the grown-ups is 27 times. This is only second time today. So we'd like to study white dwarf stars because they're a common endpoint of most stars in the universe. They have simple structure. They're great cosmic lab for high energy physics. And the evolution is more or less dominated by cooling, although there was a little bit of complication that was mentioned at the start of the session. But still, most of the white dwarf stars will just evolve and cool and get dimmer and dimmer, make them really excellent independent chronometers to other ways of dating things in the universe. Okay. All right. Oh, I'm sorry. This is this afternoon's talk, I think. This is not the magnetic talk. Can you quickly change it? It's
We're busy looking at it. We're looking if we have the other version.
there was a 2. I uploaded 2, and one is called this one.
We are busy on the computer loading it. Just give us a sec.
Okay, yeah. All right. Okay, so I'll just continue because I only have 7 minutes anyway. So when things like big survey like Sloan happened, we got more than 1 million redshift. We also, multiply many things, and that includes white dwarf stars. We have more than 10 times the white dwarf stars than we did before last century. And some of them, white dwarf stars, have magnetic field. And so that's the topic of my talk. Okay, so the one of the great things about having lots of stars is that you can do a group look at trends and as a group property, which you couldn't do when you only had handful. So yeah, okay. I started with the same slide, so that's why I got confused. So sorry. Okay, and right. So we found oodles of magnetic white dwarf stars as well. And so where does the magnetic field of the comes from the white dwarf stars? And so there's always been thought that the AP stars, if you just evolve them into single white dwarf stars, they should produce a good massive good strong magnetic field white dwarf stars as we observe, except for there's more white dwarf stars with magnetic field than there are AP stars. So it's probably one of the channels, but can't be accounted for all of them. And then there's binary evolution. We do see intermediate polars and such so we do know that there's CVs with magnetic field. And so they probably will produce a magnetic white dwarf stars at the end that we might be observing. And then there's also as the white dwarfs cool, as it gets cooler and cooler, there's different physical processes in the star that dominates. And it's, convection and crystallization is also thought to perhaps produce magnetic field. So all these things, it's hard if you have like one or two, a handful of white dwarf stars and say like, where did you get your magnetic magnetic field from? But when you have a group of them, you can look at the trends and such to see if you can actually pinpoint that which avenue magnetic field production system seems to be likely scenario, or probably all of the above, and more. Okay, and so I probably don't have time for going through some of the group properties of it, but I'm just going to highlight that in this side is the magnetic field and then the number of white dwarf stars with magnetic field that we found in Sloan. And you can see like the smaller field, we found loads of them, and then not that many for the high field ones. And then the right-hand side, the smaller blue hatched one is for the 20 parsecs volume limited sample that didn't see necessarily that kind of a trend. And it makes sense because when you're looking at a Sloan, which is more like a magneted brightness limited kind of a sample, you're going to see some of the brightest, but even further away white dwarf stars, and not just the close ones. And those that is the further away ones that is bright means it's probably bigger, which means like because it's the degenerate matter, they're the less massive ones. So we know that we have certain kind of bias, and we worried about that. We also know that the signal to noise of the Sloan spectrum is about 13. That's not great. And so when you have a not so good signal to noise and you're looking for Zeeman splitting, that could be tricky. And so we did an experiment and we found that like it tend to be conservative. So we, instead of assigning what was magnetic white dwarf star to instead we thought it was people assigned it to be massive when we did a control experiment. So we know that we have these bias a little bit, but we didn't know how much our group of magnetic white dwarf stars are biased. So we wanted to just take a look at sample of them. We couldn't do all 800 of them, but we decided to do some of them. And for that, we use a Gemini. We have 2 telescopes in north and southern hemisphere. Sloan targets are all in the north, but we can get the equatorial targets from the south as well. It's Q, so it was a very convenient way to observe. I wanted to let you know that Gemini has partner countries, but US has open sky policy. So if you don't have access to Gemini from your country, you can always apply through the US time. This is also true for the DD time. So and the next call is September 1. So if you're interested, just please go and look at it. The observation was reduced by dragons, which is our, we're moving from IRAF to dragons. Was rather important to me because when I did the IRAF reduction originally and sent it to collaborator to take a look and fit it, he told me that something is very wrong with all the continuum of the reduced data. And it turns out that we think that there is a little bit of scattered light inside the instrument, GMOS, and that was not easy to be calibrated out. And now that we knew that, I was able to go back to the Dragon's development team, and then they were able to fix it so that the red is from Dragons, but the green is the IRAF, and blue is the original Sloan spectra. So you can see that so I would like to recommend that you reduce your data with Dragons, even though you might love IRAF from the old days. Okay, and so I'm gonna show, I'm not done with all the reduction, but this is some of this is the power of the 8-meter telescopes. It's just so much better. So we can see that definitely there's a nice Zeeman splitting. And this is definitely not magnetic, but they're massive. So, and I picked those three because these are in the instability strip, so they're likely to pulsate. So these are likely to have a crystallized core inside pulsating white dwarf star. So they will be good to go and study to further understand the crystallization mechanism in the white dwarf star. So I picked these for that. And then we also saw that this star we observed it took 4 exposures on two exposures on 2 different days and 20-minute per exposure. It was clear that it was the line, the Zeeman splitting was changing. It's not only in the depth, but it looks like in the width. So it would be great if I can also go back and get the time scale of it. It's not the first time people have seen magnetic field vary, but it might be spots and whatever, but it would be good to just go. And the bottom is what the combined spectrum looked like, which is what we did when we were looking at the Sloan spectrum. Now this one has a Zeeman splitting and it looks massive, but a little bit too massive to be true. So Detlef was fitting this with a log G of 9. So this is like 1.35 solar mass, and it's not quite doing the width. So the Stark broadening and Zeeman splitting both broaden these lines, so which always makes it a little bit more complicated. But so this one is like, is it possible that we just got unlucky or lucky and we got 2 white dwarfs in the line of sight? Is this like a combination of it? So I don't know, but so that's one of the things. So this is, we're not done. We'll just look at all the 30 objects we did and see how poorly we did in our original assignment as a magnetic or not. And then we'll hopefully get back to you with analysis as a better analysis of the group studies of the magnetic white dwarf stars. Thank you.
Thank you so much. All right, do we have any last questions? Jörn?
This is very interesting. I just want to remind you that we are now getting strong evidence, some disseminations of magnetic fields in red giant stars from astroseismology.
Okay.
So we're beginning to see sort of the evolution sequence from field production in main sequence stars through the red giant phase and then on to the white dwarfs.
That's awesome.
I think that's wonderful.
Yeah, we'll get a full picture.
Yes.
Yeah.
All right, let's end it there. Thank you so much, and thank you for dealing with the technical difficulties as well. So let's thank all the speakers. And that's the end of this session, and we'll be reconvening here at 1:30.
Right? Can you go to the slide? Can you play that slide? No, just play the slide.
Not checking as in okay.
Why it doesn't matter? Just
No.
No, I said we should continue with the screening.
Perfect. Yep. Perfect. Okay. It's working great.
Which one is it?
The second one.
This one.
The second one. That one. Yep.
Okay.
Yeah, because you say that we're on. That
You may want to add my last name or something just to make it easier.
I'm gonna do that now. Yeah.
Actually, Taiwan was the first Chinese place that I ever visited. And there was a crowd of astronomers from continental China at the conference. This was on small telescopes, the last IAU colloquium.
Somehow I don't think this random
motion is going to improve things. Okay.
Does everyone fit in right?
Maybe we kind of move in together, you know, folks, as we kind of get together a little. Just saying, just with an idea, crazy idea.
Oh, if you don't see the objective, you will not.
Oh, come on, Andre, get your butt down here.
Hello, hello. If there's anyone online, if you can hear us, can you turn your cameras on? Because we're trying to take a photo. Hi.
He's way bigger than all.
I know.
It's not just me, is it?
I'm gonna sit down and put her on my camera.
Maybe if we could have the IAU figure in the main screen and then just the people in the smaller screens, maybe that would make more sense.
Apologies, we can't do that preset.
Can't do that.
It's either the Zoom or the holding logo. Maybe we can do two pictures with this.
Yeah, maybe one of each.
Yeah.
Here, I'm seeing you.
Okay, big smile. Here we go. The gentleman on the screen, I also want you to smile, please.
Yorick, smile.
Nice one, another one. Big smile, another one, 1, 2, and
Yeah, the screen's not gonna like that.
yeah, got you. Last one, can we get the open slide on, please?
I suggest you.
Big smile. And 1, 2, and 3.
Take one without the flash on. Because of the screen.
Going up, go.
You're gonna have a big white block behind it. Behind it.
Come down.
Nothing. Okay, that didn't go anywhere.
I need to see your gorgeous faces.
Hey, one more running.
Too late. I'm out here.
It's too late, yeah.
We didn't get the time off. Okay.
Here we go, and 1, 2, and. Thank you.
Okay, right. We have a very tight session today. So all speakers must get themselves a microphone as soon as they can. Definitely before the end of the previous talk, please. I'm Chris Tao. I'm chairing. And our first speaker is Stephen Bloemen. Yes. Hi. Thank you.
Thank you. So I'm Stephen Bloemen. I work at Radboud University in the Netherlands. And I was asked last minute to fill a little gap in your schedule, which I'll be happy to do. So I'm going to talk to you about BlackJam, the BlackJam array. You can see a picture here. It's these 3 telescopes in the clamshell domes in the front of the picture. BlackJam has a sister telescope, which is called Meerlicht, and the South Africans among you will probably have heard of that. This telescope is located at the SAO site in Sutherland, and it's an identical telescope to BlackJam. But Meerlicht consists of 1 telescope, and BlackJam consists of 3 of these same unit telescopes. These are installed at the ESO site in La Silla in Chile. The goal of BlackJam is to follow up the LIGO-Virgo detections of gravitational waves and to find the electromagnetic counterparts of these systems. So it's designed to do that. The problem with these detections is that they're poorly localized, they're faint, and they're relatively short-lived. So you have to look in a largish part of the sky for a faint source, and you have to do it quickly. This map here shows a few examples of these error boxes that the gravitational wave interferometers spit out. So this is what we built BlackJam for, and each telescope consists of a single CCD camera. It's 110 megapixels. The telescopes are 65 centimeters, and they cover a 2.7 square degree field of view each. So we have 3 of these, and the PI who is also here is Paul Groot. As you can see, it's a large consortium, so there are various partners that have bought into the project to do all sorts of different science cases, not just gravitational waves. One of our unique features is that we have 6 filters. It's a Sloan set and then an extra wideband V+R filter. And we can very quickly change between these filters. And that is something that many wide field survey telescopes cannot do. So we can really take several colors in succession without losing too much time. So that's one of our defining features. Our limiting magnitude is currently 21.6 in our wideband in a 1 minute exposure. And we have an image quality currently just above 1 arc second, but we're pushing that down to 1 arc second. This is an image here on the right. I hope that the video works. So this is one single image, 1 60-second exposure. And as you can see in the dense fields in the sky, of course, you get hundreds of thousands of objects in a single picture. Our image processing derives all the photometry for these sources. It's completely tied to Gaia, so we have astrometric and photometric calibration based on Gaia DR3. Now we have 2 pipelines. One serves the people that are interested in variability. So there we do forced photometry on all the positions where Gaia DR3 has the source. That gives us about roughly 100 million detections, measurements per night. And then on the other side, we have a transient pipeline, which uses difference imaging. And there we look for new objects, of course, by subtracting an older image taken on the same position on the sky. And this gives us a few thousand candidates per night. And then we have artificial intelligence pipelines to find the interesting sources in there. Now, not everything that comes out of this transient stream is real. I'll show you a few examples. Here we have the new image on the left. In the middle is the reference image taken at an older epoch. And then in the difference, you clearly see that there is this faint source in the middle, which now pops up. So this is a real source, but not everything is real, as I said. Let's look at the top example. Anybody, any idea what we see here? You can shout. It's almost, this is an airplane. So you can see the stripe, and then when the lights on the wings blink, you can see this dot, and this was picked up as a source. The one on the bottom. A UFO, did I hear that? Yeah, that's what I hear in all my public talks. I wasn't expecting it here, but it's not a UFO. This is just some electronic true print from a saturated source on another part of the CCD. But so our artificial intelligence pipelines need to tell these apart from the real sources. And we have a citizen science app to also allow the citizens and everybody here to help us with that. We also had a press conference on that earlier today. So Black Hole Finder is in all your favorite app stores. And with that, you can help us to sift through all this data in near real time. So 20 minutes after the data has been taken, it's available in the app. Let me end with a little explanation on the surveys that we're doing with BlackGem. So of course, the highest priority thing is the gravitational wave follow-up triggered by the interferometers. For that, to allow us to do that, we also do a Southern Sky survey to have our own reference image to do the transient search. Then there are transient surveys that is mostly extragalactic transient, serving the supernova communities and the likes. So here we're surveying 700 square degrees at more than 200 epochs per year in 3 color bands, always including the U band, because that is a band that's very useful for early explosive transients and that many other surveys are not doing. And then there is another almost 3,000 square degrees that we image once a week. And then probably the most interesting for the crowd here is our fast synoptic survey. That's also something that really sets us apart from surveys like LSST. This is really tuned to astroseismology and to compact binary work. So here we do a 60-second cadence for several hours, cycling through the same filters, and we will cover 1,500 square degrees per year in this fashion. And to end, just one example. So this is, for example, an eclipsing double white dwarf. You can see that we find that in our 3 light curves in the 3 colors based on 2 nights with 3 hours of data. So this is a 40-minute system. And if you want to know more, here is the paper on arXiv. Thank you.
Thank you. Thank you very much. Do we have any questions? There's one up over here on the far side.
Hi, thanks for your nice talk. So how young can you detect new supernovae or transients with BlackGem?
How young?
How young? Like young supernovae, how many hours from explosion or that kind of
well, in principle, very, very short, but you have to be lucky, of course, that you catch it early. They're always brighter in the blue, so that's also why we have this this U band. But detecting them early in the first few hours is one of the science cases that people, especially here, the institutes in Israel, are working on. But it's a matter of being lucky, of course, how early you can find them.
Any questions online? No? Okay. Thank you very much. Let's move on. So we now have Jorik Vink. Jorik is joining us online. So hopefully this will work smoothly. Jorik, please go ahead.
Hi. Can you see my slides? Can you see my mouse?
Yes, we can see your slide. We can see your mouse.
Oh, great. Okay, yeah. Sorry I can't be there. Except extremely large during the pictures. I felt a bit like Ed Harris in the Truman Show. But, right. X-shooting Ulysses. So Ulysses is a director project on the Hubble Space Telescope, 1,000 orbits for both 500 orbits for T-Tauri stars and 500 orbits for massive stars in low metallicity environments. And it is mostly the LMC and the SMC, and a few in even lower metallicity galaxies. And we will hear more about that from Grace Telford later. So massive stars, of course, they make supernovae and they provide a lot of mechanical feedback, but also the winds provide kinetic energy because the wind velocity is very high. So the kinetic energy goes with the velocity squared. So a lot of mechanical input from massive star winds. Massive stars are very hot and they produce a lot of ionizing feedback, which is interesting for star formation locally, but also at high redshift. In the cosmology, we think the first stars were massive, and we really need to understand the properties of stars very early in the universe, which are massive and which have low metallicity. Chemical enrichment is not only from supernovae, but we now see at very high redshift, large amounts of nitrogen. There's a nitrogen crisis at redshift 11. There is a nitrogen line detected here, nitrogen 3 line, that suggests a supersolar nitrogen enhancement that must come from the CNO cycle. It must be from massive stars, almost certainly, I would say, and probably even very massive stars, but that's another story. But we want to understand where all this chemical enrichment comes from. This is probably already during the hydrogen burning, so this is from stellar winds and not from supernovae. And the winds set the evolution of the star. So if we want to understand black hole masses with gravitational wave events, we need to understand stellar evolution, binary evolution, and stellar winds as a function of metallicity. For instance, the record holder is GW 190521. There was an 85 solar mass black hole, and it could be that this was a single object. And that is most likely that you get such a heavy black hole at lower metallicity, where the winds are weaker. So what we really need is mass loss rate as a function of all these basic stellar parameters. The wind properties can be obtained from the ultraviolet, but the stellar properties, you need the optical and the UV. With Hubble, we get things like very interesting P-Cygni lines like carbon-4, where from the blue edge of these lines, you can determine the terminal velocity quite accurately. You get a handle on the mass loss rate, but it's not very accurate. If you want to get accurate mass loss rate, you also need recombination lines, such as here in the optical. There's an H-alpha line. That's a recombination line and gives you information about the mass loss rate, but also the clumping properties of the winds, because these winds are not stationary. We need to understand the clumping in winds. And for all that, we need UV and optical. Also, we need the optical to get the stellar parameters. Especially log G determination is very uncertain from the UV. Varsha Ramachandran has shown in this paper that you really need the Balmer lines to get an accurate log G determination. So the project is well on the way. We have already about 10 papers, but the first two kind of describe the project and the advanced data products that can be obtained by everyone in the entire world. So we have a large collaboration of like 100 people. Anyone can join, but you can also use the data yourself for your other purposes. And we're talking about sample sizes of about 125 per galaxy. And why is it those sample sizes? Well, if you want the stellar parameters, the luminosity, the mass, and the temperature, you already have 3 parameters. So even in a 3-dimensional space, you already want, say, 5 data points only. You're already 5 to the 3, you're already at 125 stars. So this is really the bare minimum that you need to do this properly. And we really want to do this homogeneously, because there have been previous studies of massive stars in the clouds, but the studies have always been very heterogeneous. 3 stars here, 2 stars there, some with this code, some with that code, some with this type of data, high resolution, low resolution, only UV, only optical, UV plus optical. We want to do this heterogeneous, wide wavelength range, high quality data. And we do benchmarking, and I'll come to that. So some early science results, mass loss rates versus log L. For the LMC stars, we have clearly higher mass loss rates than for the SMC. And interestingly, there seems to be an indication that in the SMC,
1 minute left,
it's much steeper than in the optical. Yeah. Also, the mixing is probably much more efficient in the SMC than it is at higher metallicity, which suggests rotational mixing might be relevant. That is metallicity dependence, but as I said, there are other parameters like temperature, and there are predictions of how the mass loss rate changes as a function of stellar evolution. And if there was no bistability jump, they would collapse. But what we see is in the predictions, we see jumps in the mass loss rate. And we don't really see that back here in the data, at least not a strong mass loss rate, but more maybe a smaller bistability jump in more in line with the Kratichka results. So these results are going to come out in the next, or are already out today. And what we really need to understand is, why do the models and the data not agree? We need to understand the winds better. That means we need to understand the theory. The theory is 50 years old, but there are still many questions about clumping in winds, about how things vary between relatively low mass and relatively high mass stars. So
time to stop, Jörg.
Right. I will just say that we are benchmarking these stars, and that the parameters are quite accurate in terms of the stellar parameters, but that for the mass loss rates, we still have some discrepancies with different prescriptions. So thank you for that.
Questions for Yorick, please. Yes. Down here on Jan.
Thank you. That was very interesting. What about the effects of rotation? Do you see any of that in your analysis?
Yeah, we determine the rotation velocities. For relatively slow rotators, we also have an additional project with even higher spectral resolution, Mike Magellan, to get rotation rates. And indeed, one of the things we're interested in is how things vary with rotation rate. At the moment, more generally in the field, we still do not really fully understand how the mass loss rate depends on the rotation.
Is Thomas Nordlander ready for his talk? Yeah. Any more questions? Anything online? No. Okay. Thank you. So Thomas Nordlander is the next speaker.
Yes, so I'd like to start by thanking you all for coming, and I'd like to thank for the opportunity to give this presentation to you all. In just a minute, I guess. So I might as well start by saying that this is based on work led by my PhD student, Wei-Shen Oh, and you'll get to see how his name is spelled in just a moment. There he is. There, thank you. So jumping right to it, I'd like to convince you that the oldest stars are very useful, and they're very interesting, and they're interesting to you. So this is my timeline of the universe, of its chemical evolution, starting at the Big Bang, where only the light elements were created. So hydrogen, helium, a little bit of lithium, and jump forward 100 million years until we get the first stars. So the first stars are interesting to all of astronomy, of course. They are the first ionizing sources, and also they created the first heavy elements. And these were distributed in winds and in their supernovae. So there is a gap there of about 100 million years. We don't have so much information except the cosmic microwave background and all this. But once the first stars had made the first heavy elements, those were incorporated into the gas from which the next generation of stars were formed. And these are still, these were much more numerous than the first stars. So some of these are still alive today, and you can find them in our galaxy and in the LMC and other galaxies. And it's from these stars that the first galaxies were formed. So of course, all of the rest of the universe is off screen here, but hopefully that is interesting to you, and therefore this is interesting to you. So the context of how to use the second generation stars is this. So on the left, I'm showing this diagram of as a function of initial mass on the x-axis and metallicity on the y-axis, the final state of a massive star. So between about 10 and maybe 40 solar masses, most stars die as core collapse supernovae. There's probably a gap between about 40 and 100 solar masses where stars do not explode. These are failed supernovae. If those stars do anything, it might be as hypernovae. And if you jump up even higher to about 140 to 260 solar masses, those probably ended their lives as period-stability supernovae. So that's the picture at the very low metallicities. And on the right, I show predictions of, for each of those cases, what kind of chemistry should have been produced in the supernovae or distributed in the supernovae. And each of these has a very unique, distinct pattern that we can identify in second-generation stars. So if you find a very low metallicity star and you find the abundance pattern I show on the top, then you can figure out that was a faint supernova. You can even figure out roughly the mass of the star that should have exploded and made that. And you can reconstruct the image on the left, and you can figure out what was the mass distribution of the first stars. What was the distribution of the numbers of different types of supernovae? So this is the goal. We sometimes call this galactic archaeology. So in this work, I'm jumping right to the conclusions. On the left, those are the results of my student Wei-Shen Oh's search for very metal-poor stars in the Large Magellanic Cloud. Those are the F-H metallicities. Those are the lowest metallicity stars known in the galaxy at the time, up until Christmas Day when someone scooped us. And on the right, those are the abundances of these stars. So each panel is one star. Each symbol is a given element in that star. And the solid lines, those are reference lines for the Milky Way. So those are average abundances in the Milky Way at the same metallicity. Wei-Shen did a smart thing. He highlighted in red if abundances are discrepant by half a dex. And I just want to point out that every star in his sample at metallicities of above 1,000 thousandth of solar is a weirdo. It has at least one element that is discrepant by half a dex, right, which is huge. So we're seeing huge inhomogeneous chemical evolution in the early Large Magellanic Cloud at a level that we only see in the Milky Way at maybe a factor 10 lower metallicity. So each star has a very peculiar abundance pattern. You can tag it back to what I just talked about. And here are the results of that tagging. So the top one, probably that is a spin star. It has a very high barium to europium ratio. We think this happened in first stars with zero metallicity. They were extremely rapidly rotating, maybe 500 kilometers a second, much faster than you see today. That causes some kind of deep mixing, leads to a type of S process. The next two are R process enhanced. I'll return to that on the next slide. Below there, we have a hypernova, huge zinc abundance, almost no strontium and barium. Toward the bottom, that's a nitrogen and sodium enhanced star. Probably the progenitor was a fast rotating massive star. So you can take these individual stars and tag them back to what were those first stars in the Large Magellanic Cloud. And you can start doing this work. Part 2 of my talk is about the R process specifically. So here is a summary of what we know about ultra-faint dwarfs in the Milky Way periphery. So these are the abundances on the left of barium and on the right of europium for 10 different ultra-faint dwarfs. And highlighted are the only stars that actually contain any of the neutron capture elements. So all of them are in the same galaxy. All of them have metallicity above -3. The stars below -3 do not show this. So it smells like something that is rare. It has a delay time, neutron star mergers, probably. And the picture is that probably this only happened amongst these 10 ultra-faint dwarfs. It only happened in one. It only happened after it had reached a certain metallicity. So it's telling us something about both the rarity of those events and about the time delay of those events. And the corresponding picture in the Large Magellanic Cloud, all the symbols here are for the LMC. The gray points are for the Milky Way as a reference. These stars, based on Wei-Shen Oh's work and also Anichiri's work, are showing that the lowest metallicities between metallicity -4 and -3 don't really show any neutron capture abundances, or they are consistent with normal supernovae. Only when you reach a metallicity about -3 do you start seeing them. Thank you. Only after you reach a metallicity about -3 do you start seeing them, and suddenly all the stars are hugely elevated in neutron capture abundances. So something happened with a delay time. In the beginning, only a fraction of them are elevated. After a while, all of them are elevated. So clearly it produced a lot of R process abundances. And again, the idea is that there's a delay time early on, no neutron star mergers. After a while, copious neutron star mergers. And even towards present time, you're seeing a huge enhancement of R process abundances. And that brings me to my conclusions and my 2 take-home messages for you. So one is that at these low metallicities in the LMC, we are seeing huge inhomogeneous chemical evolution. It's a large star-to-star scatter. And we can trace the onset and the rise of the neutron star mergers, or whatever it is, in the LMC. And with that, I'm happy to take questions. Thank you.
Thank you. Questions? Yeah, Andre. All right, you can have it.
Thank you, Thomas. Amazing stuff. I'm curious, what is the level of the degeneracy when you're trying to go from the abundances back to the progenitors in your galactic archaeology?
I was trying to go back, but I should probably stay here. For some of them, it's very obvious. For some, it's not so obvious. So if I would say that the fast rotating massive star, deeply degenerate, because it's not clear that this is just abundances from a single event. It could be many events. It could be some kind of smooth background, like what we see in the Milky Way of 10 supernovae or so. And on top of that, you have the winds from a fast rotating massive star. So that one, degenerate, yeah. The one that is called a hypernova, probably the least degenerate in this picture. And the reason is that it is rich in zinc, but it's also poor in strontium and barium. So it must have started from a very low level, possibly zero metallicity, and then added on most of its material from a hypernova. So in that case, just based on the fact that it is poor in strontium and barium, you can probably tell that at least 90% of the material comes from a hypernova, and you can pin down the properties of the hypernova except its mass, except the mass of the star that exploded. In some cases, you can pin down the mass very finely, but not the explosion energy. So we get a little bit of rotten apples and beautiful polished things all at once.
Is Grace Telford ready? Yes. Any more questions? I have one quick question then. Do you, in the low S process stars, do you see lead?
We can't really tell.
Can't see lead.
Yeah, no, we would really need much deeper spectra. So these are near the RGB, near the tip of the RGB, but they're still 17th magnitude. So you'd have to invest a week on UVS to see lead.
The S process at low metallicity produces a lot of lead.
Yes, absolutely, and we'd love to see it.
Yeah. Right. Thank you very much. Right. And now we have Grace Telford, please.
All right. Thank you. Okay. Okay. Thanks everyone for being here today, and thanks to the organizers for the opportunity to speak. So I am going to share with you some of my work on observations of very low metallicity O stars, and I want to start by motivating the need to better understand these stars in particular. So we already heard some of this from the previous two talks, but O stars are, the hottest, most massive and shortest lived stars. And though they're rare by number, they have an outsized importance to this wide range of extragalactic astrophysics. And it's low metallicity O stars that are driving the evolution of dwarf galaxies and also of high redshift galaxies in the early universe. So the light that we are now observing from those high redshift galaxies and their ionizing photon production is coming from low metallicity massive stars. But below the 20% solar metallicity of the Small Magellanic Cloud, very few spectra of individual O stars exist. This is because we need to look to much more distant nearby dwarf galaxies in order to observe these kinds of stars. And so we do not have the observations necessary to test and constrain models of massive stars at these very low metallicities. So this is the gap that I am working to fill with new observations. And this talk is going to focus on a sample of 3 metal poor O stars in nearby star-forming dwarf galaxies. These span 3 to 14% solar metallicity in terms of their gas phase oxygen abundance. So our team used the Hubble Space Telescope's COS instrument to observe far UV spectra of these stars. Now, there is a wealth of information encoded in all of the photospheric absorption lines in the spectra, but for this brief talk, we're going to focus on just 2 features in these data. These are metal resonance transitions that are key diagnostics of stellar mass loss. So the energetic radiation produced by these hot, massive stars drives material away from the stellar surface. And this metallicity-dependent mass loss process can strongly affect the evolution of massive stars, but it remains very poorly constrained at low metallicities. So from these COS spectra, we can see just by eye that these are very weak stellar wind features. We do not see any well-developed P Cygni profiles here. So we can say that these stars must have low mass loss rates, but to quantify that actually requires more data, as Yorick very nicely set up in his talk earlier. You also need optical spectra in order to break degeneracies between the mass loss rate and other stellar properties that cannot be constrained from the UV alone. So in a new paper that we just put on the archive last week, we present new optical spectroscopy of these 3 stars observed with the Keck Cosmic Web Imager, or KCWI. So KCWI is an extremely blue-sensitive integral field unit spectrograph on the 10-meter Keck 2 telescope. And that means in every pixel in these white light images, we have a full R of 4,000 optical spectrum. And so just extracting the 1D stellar spectra from within these blue circles, we get these beautiful spectra that contain stellar absorption features that are key diagnostics of two stellar properties. First, we have the surface gravity from the Balmer line wings, and then we have the effective temperature that comes from the relative strengths of helium-1 and helium-2 absorption lines for O-type stars. And so now with these optical spectra in hand, we did a quantitative analysis of the full data set of the COS and KCWI spectra. So to do this, we ran new power stellar atmosphere models and tailored the model parameters to reproduce the full suite of stellar diagnostic lines that we observe in the optical and the UV. And from these best fit models, we can infer the key stellar and wind properties, and finally compare the mass loss rates of these stars to expectations from theory. So this figure is showing the mass loss rate as a function of stellar luminosity. Our three stars are shown here as the colored circles with black error bars, and the colors indicate the iron abundance in our best fit model for each star. Now for comparison, we're showing as these lines and squares, three different theoretical mass loss prescriptions. And the key takeaway here is that our mass loss rates seem to agree the best with the recent work of Björklund et al., which lie at the low mass loss rate end of this wide range of model predictions. Now, this is important to consider for stellar evolution models because, again, the mass loss rate can strongly affect massive star evolutionary pathways and end products. But most publicly available grids of stellar evolution models that are widely adopted in things like population synthesis adopt these sort of classic Vink et al. 2001 mass loss rates. And as you can see from this log scaled figure, these are predicting order of magnitude larger mass loss rates than we actually observe. So in my last minute, I want to very briefly highlight a surprise that came from this analysis. Really, I don't have time to get into it, but the punchline is that these two stars below 10% solar metallicity, their fundamental properties do not match expectations of single star evolution models. Basically, we measure a higher log G than we would expect for stars at the end of the main sequence, like they appear in this Hertzsprung-Russell diagram. And so either this is telling us that we are missing some physics in our stellar models at very low metallicities, or perhaps the stars have binary companions or have interacted in the past. But this is not actually a very natural explanation for the full suite of observations that we have. So if you're interested in this, please come talk to me afterward because these new observations have actually posed some new questions. So to conclude, I will leave you with a summary of my talk and also a brief advertisement for a new observing program that is expanding this analysis to a much larger sample of stars. TEMPOS is a new Cycle 31 Hubble Space Telescope Treasury program that will assemble a data set of almost 30 O stars with UV and optical spectra. And this is designed to complement the Ulysses and XUU data set that we heard about from Yorick before. So we will be in a position to calibrate stellar models down to very low metallicity. Thank you.
Thank you very much. Questions for Grace?
Thank you very much for the presentation. My question is, what do you mean by radiation-driven winds contribute in mass loss?
So basically the ionizing and UV photons produced by these massive stars carry momentum, and that momentum is transferred to the outer layers of the stellar atmosphere via these metal resonance transitions in those parts of the spectrum. And so that momentum is able to actually remove material from the outer parts of the stars. And so they actually decrease in mass over their lifetimes.
Thank you. Another question up at the top there, please. Yeah.
Hi, thank you for the very interesting talk, by the way. Very interested in these low metallicity models. Now, do you have any idea what sort of the rotation rates are based on the spectra of these models?
Yes, so the two lower metallicity stars both appear to be at least moderately fast rotators. Exactly how fast is a little hard to say. It's sort of model dependent, and the resolution of our spectra is not really high enough to do sort of the state-of-the-art Fourier transform-based V sin I measurements, but they must be at least 200 kilometers per second V sin I.
Right, very interesting. Thank you very much.
Mm-hmm.
Here, so is Douglas Moyani ready? Yeah. Another question while going.
Were you able to measure the carbon and nitrogen abundances?
We were able to constrain those abundances, I would say. Yes, I think they're not inconsistent with the initial guesses that we adopted based on typical nitrogen to oxygen and carbon to oxygen ratios in low metallicity dwarf galaxies.
Yeah. Well, in interacting binaries, you always see an overwhelming overabundance of nitrogen and sometimes virtually no carbon.
Right. So we have one star that appears nitrogen enhanced, but it's the one that is a slower rotator and doesn't seem as problematic.
Is that the one in WLM?
Yes.
Okay. Thank you.
All right.
Okay, thank you. Right, let's move on now. So thank you again. Next speaker is Douglas Moyani.
Okay. Hello, ladies and gentlemen. I am Douglas. Today, I'm going to be talking about some of the work that I did with Prof. Ferreira, which was to investigate the lambda Cepheids astrosphere. Okay, good. I don't know. Let's go. This thing's slow. All right. Now, what is an astrosphere? An astrosphere are basically these large-scale structures which are created by the stellar outflowing wind when it interacts with its ISM. The structures was for a generic star was fundamentally for a generic star. Cher actually proposed a model in which he showed us the schematics using a hydrodynamic model, which he was able to show that the structure composes of a termination shock and an astropause and a bioshock. There's a large scale area between the termination shock and the bioshock, which is known as the astrosheaf, which composes of two areas, which are the inner and the outer astrosheaf. And for this work, what we basically tried to do was actually to model the lambda astrosphere, and which is a blue supergiant with a spectral of 06.5, and it has an apparent magnitude of plus 0.5 in the V band and this luminosity. Its distance from our F to it is around 617, and it was observed by Balmer. Sorry, these are some of the parameters which also they discovered, and it was observed by Balmer and a few others, and they were able to actually show these images right here, which were able to confirm the bioshock as well as the astropause existence. However, due to lack of lower number of density as well as the X-ray as well as hydrogen leaf alpha's emission being subdued, they were not able to actually get the area between the inner astrosheaf and the astropause. I think I see that. Okay. So in their work, basically what they're trying to do is actually how do we actually model the entire astrosheaf, since you can't have that limitation area. And when they did so, they were able to show that if they model it using a code known as the Kronos model, they were basically able to actually model the whole stellar wind, and showing here, I'm showing actually some of their work, which is actually showing the density of the stellar wind, which if you look at these things here, it's actually the changes within the speed of the stellar wind. Now, what you can also do is if you want to find out that distribution, you can also start to model starting from this point here, going to all this, which you are actually able to show this figures, which is known as the density and velocity profile. So in our model, what it is actually not necessarily a name for it, but I usually call it the Pen's model. What we try to do is actually to compare these two models. And what we fundamentally found out is that in the inner regions, it's actually slightly the same. However, from the termination shock to the ISM, it's not the same. And this, we attributed these findings to maybe caused by radioactive cooling. And also, we also find out that if you look at this dash line, is that whenever our model was trying to figure out whatever it's trying to do and solving it within a grid line, it cannot actually solve it correctly in some sense, because you have to take into proportion whatever grid size it actually is. Because if you see here, if you increase the grid size, it's actually increasing the astropause, but if you actually decrease it, you can actually see it's actually going slightly inward. Right. Also, what we're able to show with this model is that you can actually model the astrosphere, but the primary concern was for us was that what happens if this star is actually slightly loses its velocity? Well, we actually modeled it and we show that because the star is moving at around 80, what happens if you decrease it? What we're able to show is that if you decrease it by 80, the astrosphere expands towards the ISM. And of course, due to this, the bioshock will also increase. Another more thing which you can also show the distribution. You can see that if you consider this plot here, you can also show that this is slightly, so this is more showing if you compare these two plots, which this one is from 80, this one is for 40. Now, another more parameter which we did try is the ISM magnetic field strength. Now, what we did is that we tried to compare between the two, where the ISM, where we started from it being slightly decreased to it being the way it is as it now. For the first figure, what it shows is that if you try to compare, if you decrease it slightly, it looks the same as the heliospheric magnetic field. And from that point on, we see that you can also get all the same similarities as the people who are actually, like, for example, from Parker's expression, you can actually show that you can even show the Archimedean spirals here, and also there is interaction, which is sort of similar to what Ophir saw. However, if you increase it to what the astrosphere is right now, it's actually not the same case, because you can see that it's actually compressing this figure to one side, meaning that it's actually becoming asymmetrical. This can also be thoroughly seen if you're looking at the 3D model. We can actually show that if you compress it because in this point here, it's actually when you're cutting the star between the Mediterranean and the equatorial, and we are able to show that if you cut it, this is actually more compressed to force it to be in one side. And for that, ladies and gentlemen, I would like to thank you.
Thank you. Now,
hopefully there was some
questions for.
Yeah.
Yes.
Thank you very much. So my question is hydrogen line emission induced by shock? If so, how can that happen?
No, in this case, we actually didn't even look at it, because for that, you need to consider several factors. Like, in our model is basically included, like, for example, there are 3 fluids that you need to consider. But if you want to look at it from an overview point of view, you need to consider 5, in which that will require a bit of like nitrogen thing, which was only shown by zinc. And that guy doesn't want to give us his code. I don't know why. Why scientists do this all the time? Like, can you please explain? So no, I don't know. I can't answer that one. Sorry.
Thank you. Any online questions? Sorry. Question. Is post going ready? Yep.
Yeah.
Any last question? Oh, okay. Thank you. The next paper is post going.
Okay. So thanks for the ability to come and give this presentation. This is an introduction to a mission called Polestar that a whole bunch of us are in the process of defining and preparing to propose to NASA next year as part of their Small Explorer opportunity. So cutting to the chase, it's a space-based experiment to understand the environment of massive stars and how they affect their evolution, specifically by looking at the issue of rapid rotation. Because we're going to be using spectroscopy to do what we need to do, it's a spectrograph, but mounted behind a system that allows us to extract the polarimetry of the emission that we measure. So it's going to provide, or it's being designed to provide, the kind of vital information necessary about characterizing the stellar environments, the mass loss, the wind velocities, the clumping, many of the things that you've heard mentioned in the last few talks. For a variety of different massive stars, standalones, binaries, those engaged with disks around them, so on and so forth. So by adding polarimetry to the mix, it allows us to break some of the degeneracies, for instance, about tilt and rotation speed, but also a number of things in terms of understanding what's going on at the equator versus the poles by applying techniques like the Oman effect. But also by adding a system that can measure all 4 Stokes parameters, it allows us to analyze and separate the role of magnetic fields in the wind zone by going after those very same resonant FUV lines that you heard mentioned by Grace. So taken together, these tools are going to provide an unprecedented suite that will open a new view on the universe. Now, for this particular audience, I'm preaching to the choir that massive stars are sort of important to understanding what it is that we want to understand about galactic chemical evolution. They are absolutely critical in the definition and the propulsion of the ecology of star formation through the baryonic life cycle. But while there's a whole suite of different theories that predict very profound and yet very different consequences for the role of rapid rotation, including things like binary mass transfer and stuff, there's not a heck of a lot in the way of observational constraints. So we're seeking to provide that in the best traditions of observational astronomy. And so the idea is to put on the table UV spectropolarimetry to capitalize on the aspherical geometry that results from rapid rotation, and to use the tools that I've touched on very briefly here to give the kinds of information to constrain what's going on, and then to understand what that means for the internal structure of the stars themselves, and what that means for the mixing rates, the gradients, and what that means ultimately for the evolution of the star. So we've defined a suite of rather bright, because this is a small explorer, so it's going to be behind a relatively modest aperture in space. But our various programs and hypotheses are driven us to a sample of about 349 suitable targets within about 20 to 30 parsecs that while required for our science sample, and will define the observation sequence that we would follow. We will go back and look at multiple epochs as these rapid rotation systems rotate under our line of sight. And because we're mapping not only what's going on at the surface, but in the wind zone, we'll be building 3-dimensional tomographs as these systems rotate under our line of sight. So we're looking for high phase coverage. We're looking for the necessary observations to constrain rotational and orbital dynamics. So the kinds of things that we're going to be going after, of course, are the immediate outcomes of rapid rotation, the oblate shape of stars, the propensity to lose material at the equatorial region, to understand mass transfer between binary systems, to understand what the potential role of strong or intermediate magnetic fields might be on breaking of the rotational system, and providing some kind of connection between an existing disk or just the environment itself. And many of these things are going to constrain asymmetries in the star itself, and so they have implications for end-of-life state for these stars and when they ultimately go supernova. So there's a whole suite of different target class types and theories and hypotheses that go along with it within the science program that we're currently crafting. And a lot of what we are doing is driven intimately by the decadal survey from the United States, both in the 2010 and 2020 versions that lead to a number of different things that we're seeking to gain insight to, such as application of realistic geometries as opposed to spherical cows, and looking at leveraging space-based UV spectroscopy to gain understanding, for instance, of binary stellar evolution, but also stellar surface features and mapping magnetic fields and what that means for rotation and the wind zone connection to the internal structure of the stars. Ultimately, we seek to gain a better understanding of how stellar lives and their impact on cosmic evolution is affected by mass loss, rotation, and stellar evolution. So Polestar's going to be bringing to the table spectral diagnostics. It's going to have enough spectral resolution to see the loss of mass. We'll be leveraging polarimetry to bait degeneracies and observations, provide time domain mapping, and look at a variety of different ways at looking at what's going on between the pole and the wind. And all of these will provide the kinds of information listed on the right that will give us information immediately necessary. The specific design itself is a very simple one moving part system that uses a rotating modulator to leverage and measure all 4 Stokes parameters. It does so by converting the polarization to intensity, so you can increase your signal to noise simply by integrating for longer. The technologies necessary are all at TRL6, with one exception that will be flown on a CubeSat next year. We'll be looking at a spectral resolution between 15 and probably 20,000 and leveraging a wavelength range from 122 to 320 nanometers behind a 40 centimeter aperture. So we're going to be using UV spectral polarimetry to try and give us a better understanding about how rapid rotation is an important thing, and look at using that discriminatory information to break the models between theoretical predictions. And we hope to bring an entirely new way of looking at this class of object to the table. Thank you.
Thank you. Questions for Paul? Questions online? And we have a question up there behind you.
Hi, thanks for the very nice description. I guess the mirror diameter you're talking about is fairly similar to what's on UVOT on Swift. So you could imagine, if you didn't care about spectral resolution, binning this down and using it for quite a wide range of transients and things like that. Is that something you're considering, or something that you could think would be feasible?
There's any number of different things you could use this for, right? The idea when you sell a mission to NASA is you have to be laser focused on a particular suite of outcomes, and that's what I'm presenting to you here today. But yes, there's an awful lot of people who are like, ooh, a UV spectropolarimeter, we could use that for fill in the blank. And so there's a whole number of different people and groups who have expressed interest that would go in the enabled science section of the proposal. But the kind of application that you're describing, yes, that's exactly the kind of thing. We haven't really designed the system to be as quick in terms of responsiveness as Swift is. But if that becomes a community prioritized capability, then we can revisit the capabilities of the spacecraft bus.
Thanks. Thank you. Any other questions? I think not, so thank you very much.
Thank you.
Speakers on the Persia. Please go ahead.
Thank you. All right, so I'm another gap-filling talk. So I am entirely excited to talk to you about the effort that we've been putting in the last year or two in trying to solve a massive amount of binary star data that is presented. So I will try to make a case here that uses eclipsing binaries as an example, but hopefully you'll see that you can apply it to your science as well. So let me first introduce the royal road of eclipsing binaries. Most of you probably are aware of that. So eclipsing binaries serve as the fundamental calibrators of fundamental stellar parameters such as masses, radii, temperatures and luminosities. The way that works is we start with radial velocities, or if we have interferometry, that gives us masses. If we find eclipses, then purely from geometry, we can infer what the radii are. If we have spectra and or color indices, we get the temperatures. And then finally, from distance, known extinction, and the observed magnitude, we solve for the luminosities. Now, of course, let me say that this is highly idealized. And so the devil's in the detail, which means that when you actually go about modeling this, for anyone who's ever tried to model an eclipsing binary set of data, observables, this is a month-long process if you want to do this right. But if you do this right, this is the outcome. I'm showing you here the mass-radius relationship, where the dashed line here is the zero-age main sequence, and all of the dots here are the solutions that follow from eclipsing binary data. Note that the error bars are not missing. They are smaller than the size of the symbol on the plot. And on the right, you're seeing essentially the same plot where all the solid symbols here have been plotted with open symbols. And what you see as solid symbols are the results of interferometry. So interferometry is inferior to eclipsing binaries if, of course, you've done the job right. So now let's try to do a little bit of math of how far we can get. So if I look at the number of papers where eclipsing binary solutions in fundamental parameters are better than 3%, we're talking at around 500 as of today. If you're really good at what you do, it'll take you 1 to 2 weeks to do a single binary. And the observational data today, right now, that are available to us, I'd say, without trying to exaggerate too much, it's about 20,000. But with LSST coming online, with tests, full frame images being exploited, and so on, we're looking at about 10 million by the end of 2025. So if I count how many numbers of astronomers we need to finish this in 100 years, well, it turns out that we need about 12,500 astronomers. So if you're doing anything else, please drop it, because there's 13,000 astronomers in the IAU. So we all have to have you on this, right? Obviously, this isn't feasible. So I'd like you to understand that right now, the way we do things, modeling EBs correctly is the main bottleneck. And this is how we try to solve it. If you want us out of the game, just sue us for appropriating the logo. So eBay stands for Eclipsing Binaries with Artificial Intelligence. So this is our approach how to get there. We've proposed the first such scheme back in 2008 when I was still a postdoc. Now, allow me just a minute to try to explain how neural networks work. If you think it's a fundamentally difficult concept, I hate to disappoint, it's not. So in the next couple of hours, I'll explain how this works. And so what you do is you have an input layer where your observables go in. That needs to somehow be mapped onto the output layer, which is what you want to learn from the system. And so the actual neural network's nothing but a mapping from the input layer onto the output layer. And the way you do that is you add another layer, intermediate layer in here. So how does that work? All the values that you put into the input layer get propagated first onto the hidden layer, and then from the hidden layer onto the output layer. It's just a weighted set of connections, essentially, that you need to add a little bit of nonlinearity to it so that you can properly map input to output if it's a nonlinear mapping. And that's what we call the activation function. So what you do is you connect all these values through these weights on each of these connections. And the neural network, when you present it exemplars to learn from what it sees, it'll give you the estimates of the values that you have. So the obvious choice might be to put a light curve in here to train the network to give you your output parameters out there. But I'm trying to propose something different. What I'm proposing is the following. You have a model that takes some time. For example, in our case, a forward model can take upwards of 2 minutes to calculate your observables. So instead of putting your observables in here, put the model parameters in here, propagate those model parameters so that you get the observables on the output layer. In consequence, what you'll be able to do is replace your model, which is computationally intensive, with a neural network, which is cheap to calculate. So a forward model takes about 2 minutes. A forward model with this convolutional neural network, it's about 10 microseconds. Now, you can say, well, 2 minutes isn't that big a deal unless you have to do it millions of times, which you do if you're trying to sample over your parameter space. So in consequence, you need high performance computing, or you can shave off about 6 to 7 orders of magnitude. But you see that this is exactly what we can do. So the question is, can this convolutional neural network replace the physical model reliably? Can we get there? Let me show you. What I'm showing you here is the sampling of the parameter space, where in red and cyan, you're seeing the best backpropagation network, the convolutional neural network, and the model. And you see that they are effectively equivalent. So you can, in fact, shave off 6 to 7 orders of magnitude by doing this. So 2 weeks on high-performance computing cluster becomes 10 seconds on your laptop. So finally, to summarize this in a single picture, and Chris will enjoy this. You ready for this? This is my summary. Thank you very much.
Okay, thank you. Questions for Andre? Yeah,
In the back.
there's one at the back in the middle.
And while the microphone's running, let me reiterate. Whatever model you're using, this doesn't have to be eclipsing binary model. Whatever complex model you're using, you can use this for your own data in the exact same way.
Hi, thank you for the very interesting talk. And I'm very curious to hear what sort of training you're going to be doing for these neural networks. So, because obviously one of the concerns is if you're doing supervised training, you're then potentially inputting your own biases into the answers.
So great question. What we do is a precursor to this was to build a binary population model of the galaxy, which means we used existing eclipsing binary data to try to figure out what underlying binary population has to look like in our galaxy to produce the observed eclipsing binary population. Now, when you have that, then you sample from those distributions and you build your galaxy that consists of both single stars, binary stars, multiple stellar systems, and so on. And when you pair those stars together, you get a sampling that's as realistic as possible. That is what we use as our exemplars, which means that's what we use for our training set. We synthesize the observables using Phoebe, which is the model that synthesizes observables. And we generate about 10 million of such observables. And those are the ones we use to train the network. So once, and you're absolutely right, there still may be an inherent bias in there. However, neural networks are particularly good at interpolating non-linearly and particularly bad at extrapolating. Yet this gives us the confines of our parameter space, and it allows us to check how close to the boundary of the parameter space we are. And that gives us an additional qualifier, if you will, to tell us how reliable the results may be.
Thank you. Is Lynn Hillenbrand ready? Yeah, thank you. Any other question while we're waiting? Yeah, one. Okay. Yeah. I don't see. I see it. Yeah.
Excuse me, I have one question. Thank you for your interesting lecture. Is this program suitable for use in analyzing the central star or planetary nebula in closed binary system?
if the model can do it, yes. In our particular case, the most recent addition to Phoebe has been the use of TMAP model atmospheres that extend log Gs into the SDB, SDO, and then white dwarf regime as well. So we can go down to about 9.0 in log G, whereas before we were limited to about 5.0, so main sequence. So now, as far as an embedded white dwarf in a planetary nebula is, for as long as there's a reasonable model that we can do this for. And this is something that Dave Jones was working on, if you know him. So for as long as the model can do that, of course, this approach will work, but you will have to synthesize such models to high fidelity.
Okay, thank you, Andre. Next speaker is then Hillenbrand.
Okay, great. Thank you. The hourglass here symbolizes a few things. One is the importance of time for almost everything we do in astronomy. Second, I'm talking about timescales in this talk, hours to decades, variability in young stars. And third, I don't have a lot of time to give you a description of the richness of this topic. So we'll just touch on a few things that I hope are interesting to you. As I think everyone in this room can appreciate, stars are variable, all of them. It's just a matter of what amplitude and what timescale. What I'm showing here is from the Gaia data. So this is Gaia absolute magnitude versus color. And the colors on the plot, there's a gray that is not showing here. So what you don't see here is a gray main sequence, the gray giant branch, but there's variability all across this HR diagram, and young stars occupy one of the larger amplitude ranges, aside from Mira's red and Mira variables. The pre-main sequence stars are the largest amplitude variables around, and these are stars that are contracting towards the main sequence, so they're large radii, 1 or 2 stellar radii, drop, but only in this range masses, 0.1 to 1 solar mass or so, but they're dropping down as they contract towards the hydrogen burning main sequence. And so just to illustrate what we're talking about here, we have a rotating star that's active, so it's heavily spotted and contributes, sorry, just to finish the description here, a rotating star that is spotted, it's receiving material from a circumstellar disk. So the initial stages of pre-main sequence contraction and buildup of the star through accretion, material is coming in along these magnetic channels, roughly dipolar. There's also a surrounding disk that is speeding this accretion. And in this artist rendition, we have a forming protoplanet. What radiation do we see from these objects? We see a photosphere, the photospheric emission, a large contribution from star spots that cover some fraction of the photosphere. The accretion can be modeled, but as shown here is roughly a 10,000 or 8,000 Kelvin black body that adds excess emission. And then we see the inner part of the disk, which has the dust disk gets to 1500 Kelvin. There's a gas disk that can extend interior to this that ranges out to a few tens of AU or so. And so these are dynamic. It's a dynamic region. The star is rotating. It's locked to the inner part of the disk, which is speeding the accretion from this larger disk, as I said, that goes out to a few tens of AU. And so we can use time domain data to probe these small spatial scales. And this is roughly Keplerian rotation. So mass and radius of the star are important for determining the timescales. Larger timescales are measuring phenomena that are further out in the disk. So I just wanted to illustrate some of the give you a sense for the data. So these are light curves from K2 Kepler, the K2 phase, and These are a few months, so a few tens of days. And what we see in some objects is just the periodicity, as in standard active stars. So those rotating star spots come across our line of sight and produce a periodic, or if we have multiple stars, there can be 2 periods seen from the system. But then for other kinds of objects, as I'll illustrate further, we can see this quasi-periodic behavior that is generated by phenomenon in the innermost part of that circumstellar disk. There can be variability in the accretion. There can be obscuration along the line of sight, very local in that inner circumstellar environment, that can cause these dips in the light curve. And again, these are a few months, 3 months or so. And those dips can also be aperiodic, or we can have this more stochastic behavior that cannot be characterized as periodic, or predominantly dipping, predominantly bursting, so in a more stochastic frame. This is illustrating, again, these kind of 2 categories of accretion bursters, or obscuration and what we call dippers. The left is the same. This object was shown in the previous panel, but these are different versions of this, where again, we're just seeing variability in that innermost magnetospheric accretion region, either in the flow itself, or the impact of material on the star, or something occurring in the mass loading region as material moves from the disk onto those field lines. On the right, what's shown is ground-based data. So this is cadences maybe once per day or so, as opposed to here, the cadence is about every 30 minutes. And again, this is an artist's conception of what what that variable obscuration might look like. So we can characterize this through a range of timescales and amplitudes. And the typical timescale for the periodic or quasi-periodic having to do with the rotation of the star and that mass loading from the disk onto the field lines is a few days. These timescales can go out to the duration of the survey, which was a few months or so, as I said, and amplitudes go from a few percent up to factors of several. And I've tried to, in what I'll show you here is a complicated chart that tries to organize the different observations with their physical interpretation. And I'll zoom in on what these different categories are. So as I said, we have the periodic phenomenon, which can be pulsations, rotation, or binarity, the quasi-periodic material in the inner part of the disk, and various aperiodic phenomena, extinction-driven or accretion-driven. And I'd like, in my less than 1 minute, to talk a little bit about the larger amplitude outbursting kinds of stars. So here's an example over a long duration. This is 125 years of a famous star called EX Loop that has these sort of accretion bursts, a very large one in 2008 that was well studied, another one in 2022, and a large one in 1956. These are other ground-based examples of large amplitude behavior on different timescales. So there are objects that sort of go up and down. This is 5 magnitudes in variation. This is a systematic burst, kind of like that EX loop one that I showed in the last slide. And this is a more systematic outburst of the inner part of the disk. And so we can fill out this diagram that I showed for the high cadence data down here with a range of these outbursting sources. And what's happening here is that we transition from this magnetospheric accretion into an instability in the inner part of the disk that raises the temperatures substantially, changes the spectral energy distributions, gives us a lot of excess ultraviolet and optical light as they increase, as I said, by factors of 100 in luminosity or so. And, as I said, we're kind of filling out this parameter space empirically of amplitude of the variability and timescale for the events. And what's important for star formation is to understand the frequency of these large amplitude outbursts, because it's actually contributing to building up the mass of the central star. And if you don't care about that, maybe you care about planets forming in these disks. And what's interesting here is the transition from in the peak of the planet distribution, which is an underlying histogram that cannot quite be seen, we're increasing the temperature of the disk from a few hundred Kelvin to a few thousand Kelvin, and that will have impact on these planets. And I can stop there with a summary. And just a reminder, there's lots of time domain sky surveying going on these days at multiple wavelengths, and we're learning a lot about young stars among other kinds of astrophysical phenomena. Thank you.
Is Jiangao Wang ready? Jiangao Wang is like online. Not yet. Let's just say so. Any questions? Questions for?
I'm here. Sangao Wang.
Thank you so much for the interesting talk. I'm just asking about if this could apply it for the massive young stellar objects. Thank you.
Yes, there are. There are these kinds of I'm assuming you're talking about the large amplitude outbursts. Yeah, these are also known to occur among massive stars. They're much more embedded. They're not optically or near infrared revealed, and so they're seen in other ways, mainly long wavelengths. So yes, this has been seen.
Okay, thank you very much. So we now have Xiangao Wang, who will be presenting online, I believe. Are we ready?
Hello, Wayne. Can you hear us in the room?
Yes, yes.
Can you please talk to him online just to see if we can hear you?
Hello, Xiangao.
Sangao Wang, right?
Yes, Xiangao Wang.
Because Professor Wang is something to have to deal with, so he let me to have a oral presentation here. Okay.
Okay. Can you do it?
I share my PPT.
And who are you? Hong.
Okay.
Okay.
Can you share my PPT?
Yes, you can. Thank you.
Yeah. My name is Kong Feng. So I'm so excited to have an oral presentation here. So I will talk something about supernova associated with GRB. This is my outline. Okay, first to propose a connection between GRB and SN at 1968. But the GRB 9A0425 is the first GRB case that is to be related to supernova, and GRB 030329 is the first case that has strong evidence the connection between long GRB and supernova is okay. The next one. Sometimes in general, we identify the supernova associated with GRB. We always from the light core and spectra. Most GRB associated with supernova. The light core have a supernova burn about 10 days. In general, we think the short GRB source from neutron star merging, and that associated with the kilonova, and the long GRB is sourced from massive star depth, and long GRB is associated with supernova, but have some GRB is basically is, for example, GRB 06014. This GRB have a hot discussion at 2006, and there was 4 GRB is very especially because there is long GRB, but they are was identified associated with kilonova. This is a recently observation GRB 221009A is a green east GRB today, and whether GRB 221008 is associated with supernova 2022 XIW. So some studies report that no supernova emission associated with GRB 221009. But there are also some studies think that have some connection between the 221009 and the supernova. So we follow up this case with Kite and Nick and Jurek and also GT telescope. So we have a good light core at in the R-band. So, and we collect some data in some open data.
Just 1 minute left now, please.
Okay, thank you. And we taking our data, we think there is a bump, and the energy we find the value is of the is constant with the measure of GRB, and that the conclusion is the GRB 221009A is associated with supernova 2022 XIW. So that's my that's my conclusion. Thank you. Okay, thank you.
Okay, thank you very much. Some questions for Kong Te Feng. Anyone have any questions? Are you happy to answer questions?
Oh, okay.
Any questions online? No. Okay, there don't seem to be any questions. So thank you again, and thank you to everyone. All right. And thank you for keeping on time. It's now coffee time, and there are 20 posters to have a look at. So there's much to do. And we are back here at 3:30. Okay, thank you very much.
Hopefully. Thank you. It's very full up here.
Yeah.
Yeah.
I'll get out of your hair in a second.
Let's take about the room.
Yeah. Yeah. You know, I was worried that this was going to be like way too big of a room, but today it's. Oh, it's nice.
Huh?
Yeah.
Yeah.
If that's not doing anything, then there's no difference between the PDF and the PowerPoint.
May I have your jacket off so I can?
Tino,
Yeah, please have your jacket off.
wacht voor mij nou. Wacht voor mij. Nou, is klaar.
Yeah.
Clip your favorite.
Thank you very much.
Thanks so much. Sorry for being so late.
All right, ladies and gentlemen, welcome to our final session of the Division G days. Next up is Dr. Hiramatsu. So please.
Thanks. Sounds good. All right. It's good to go. I think you can hear me. So I'm Daichi Hiramatsu from Harvard CFA. So I'll be talking about this particularly interesting supernova called 2021 QQP, which is an interacting supernova. And I think listening from the previous great talks, we all agree that supernova are interesting and important. So I'll just go ahead and introduce you this class of type 2n supernova. So those are interacting supernova. And then in supernova classification, when you see type 2, that means it's hydrogen rich. And then N stands for the narrow lines you see in the spectra. And then this is really indicative of the interaction between the supernova ejecta and then the circumstellar medium or CSM. So the basic picture is like this, that you have supernova ejecta that is interacting pre-existing CSM that is coming from the progenitor mass loss prior to the explosion. And then the shock interface forms between the supernova ejecta and then the CSM. And then this shocked shell is what we see as the null lines in the spectra. So in this case, the photosphere forms at this shock interface. So unfortunately, the supernova ejecta itself is mostly hidden because it's below the photosphere. But what's interesting here is that this shock interaction layer traces the CSM outward. So in other words, you trace. Oh, it's back? Okay, cool. So in other words, you're tracing the progenitor mass loss history in reverse because you interact with the CSM in the inner region to the outer region. So you're tracing, back tracing the mass loss history. So that's what's interesting about these interacting supernovae. And then here I'm showing a sample of type 2n supernova, their light curves, brightness as a function of time. And then it's a really heterogeneous class that the brightness spans roughly 5 magnitudes or 100 times in flux. And then the time scale spans 10 to 100 days in, So that's a really heterogeneous class, both in luminosity and in the time scale. And then in some really rare cases where the supernova happens really nearby, so that you can really get down to really deep observations at -10 in the absolute magnitude or so. So this is about the particular supernova 2009 IP. And then in this case, you can see the precursor activities prior to the explosion. So this is the mass loss activities of the progenitor prior to the explosion. And then afterwards, supernova happened, and then that is interacting with the CSM. So the big question here is that whether we can draw a consistent picture from these precursor supernova observations, and then what are their progenitor channels. And so now I'm jump onto this particular supernova called 2021 QQP. And this is the light curve in different bands from blue to near infrared. And then you see a really sharp multi-peak light curves, which is atypical for regular supernovae. And then if you look at the G-R colors, the supernova became bluer at the light curve peaks. So this is indicating the temperature is likely increasing. And then what's more interesting is that if you go back in time, and then you can see this really long gradual rise in the light curve prior to the supernova. So this is what I mean by precursor activities. And then this is back prior to roughly a year before the explosion. So this is the complete light curve of this particular supernova. And then if you compare this 21 QQP in black points with other interacting supernovae, you see this is a unique in terms of its sharp peak and then this really significant second peak. So this is a really complex light curve. So we have, and then just go through spectra quickly. As you see, this is a type 2n supernova. So you see a narrow emission lines of hydrogen. And then by decomposing the line profiles of hydrogen emission lines, you can get an estimate of the kinematics of the SN-CSM shock shell, and then also the CSM. And so these are the velocity estimates for these two components. And then since this is a complex light curve, we have to come up with a really flexible analytical modeling frame. And then what we do is instead of trying to fit the light curves with the known models, we assume that the luminosity and then the velocity measurements are the ground truths, and then try to see if we can come up with the CSM density and then the mass loss history to reproduce the light curves. So that's what's plotted here, the light curve, luminosity as a function of time. And then our assumption is that the observed luminosity is the sum of forward shock luminosity and then the reverse shock luminosity in the interaction region. And then these different lines are color-coded by the exposure energy of the supernova. So if the exposure energy is too low, this shock shell actually stalls. It just stops because there's, the energy is not high enough to propagate through the CSM. So in this case, at this point, you get the reverse shock becomes greater than the observations. You get minus negative forward shock luminosity. So this is unphysical. And then you can do the same for the velocity. So if you say, okay, this blue line is consistent with the luminosity evolution, but the exposure energy is still low, still too low to reproduce the velocity evolution. So you kind of have to have this, 4 times 10 to 15 arcs of exposure energy or so. So this is consistent with both the light curve and then the velocity evolution. And then this is what I mentioned. And then based on this, you can reconstruct the density structure around the supernova. So this corresponds to the progenitor, CSM density as a function of radius. And then you see double peak features where the first peak corresponds to the first peak in the light curve. And then the second lower density peak corresponds to the second peak. And then from the CSM velocity estimates, you can reconstruct the mass loss history of the progenitor. So you see a significant mass loss history a year before the explosion, and then another one 2 years before the explosions. And then based on this modeling framework, we can estimate the CSM mass was at roughly 2 to 4 solar masses. And then this is roughly consistent with the precursor luminosity that we saw. And then the SN parameters are such like these. And then, so the big question is, what are their, the progenitor systems, luminous barriers, partial permissivity, or some really exotic binary system? So since you guys are stellar evolution, experts, I'd love to hear your inputs in here. And then just as my summary here, so the mass loss rate is plotted as a function of expansion speed. And then norm, massive stars are plotted here where you see the red supergiants like Betelgeuse down here, and then some LBB outbursts like Eta Carina up here. And then this particular type 2 and supernova places here. So again, what's the progenitor channels that still remain unknown? But I think the future is bright that when LSST becomes online in late 2025, that's next year, we can see more of this slow and faint precursor SN, SN observations, and then it's going to increase the sample size by at least 2 orders of magnitude. So this is very interesting. And that's it for talk. Thank you.
We have time for one quick question.
Thank you very much. I have 2 questions. Okay, it's a really very inspiring speech. My first question is about, is there any investigation about the helium emission line in your study? And the second question is about the second peak in your light curve. Do you think that it could be maybe induced by shock as origin?
Yes, so to your first question, we see helium here. So there's definitely helium emission lines. And then to your second question, yes. So our assumption is that the light curve is purified by this shock interaction between the supernova ejecta and then the CSM. So yes, both peaks are powered by this interaction.
All right, let's thank the speaker again.
Thank you.
Next up, Dr. Nita, Hopefully this time they get the correct presentation. Or maybe you can give us the first one again.
Right. Yes. Okay. All right. So this time I'm going to talk about helium atmosphere white dwarf stars. By the way, this picture is Mauna Kea. It's with the Milky Way in the background. Okay, we all agree that white dwarfs are important. It's not just a standard star, which I get teased about at my work, that I study the standard star. And the HR diagram, there's a white dwarf cooling track. So it goes from, it will evolve from the hot to cool. So this is a cartoon version, really cartoon version of it. So white dwarf will evolve from the hot end towards the cool end. And as it evolves, we know that there's roughly three different temperature range in which they pulsate. This is great for us who does seismology which means that we have three different time period where we can study the structure, internal structure of the white dwarf stars as it evolves. I'm going to talk about the DBVs, or the DBs and the DBVs, which the spectrum of them are dominated by the helium-1 lines. And one of the reasons that it's really fun to study the DBs is, for instance, if you look at the bottom plot, it's the green line is the neutrino luminosity, and the blue dot line is the photon luminosity. So when it's really hot, the DBs, the energy is carried away more by the neutrino luminosity than the photon luminosity. So one of the things, if you're a seismologist, is the hope that we have one of those really hot DB white dwarf stars with a pulsation that we can measure its secular cooling through the changes in the pulsation period, which we will then be able to make sure that we got these calculations right. So that's one of the many reasons why we like to study pulsating white dwarf stars. Okay, so the interesting thing about the DBs is in the 1980s, we found that, when it's hot, you get the helium-2 lines dominated, then it gets cooler and cooler, cooler, and then the DB is a helium-1 line dominated spectrum, except for some reason from 30 to 45,000 degrees, there's no DBs. And there's no reason why there shouldn't be any DBs. And so it was called DB gap. I don't know why we don't have sexier names for anything, but we don't. So it's a DB gap. And then it was later when we found lots of white dwarf stars through the survey, we finally found few DBs inside the gap. It still doesn't account for why the number is so much smaller than what you would expect if they just all was born from the hot end and just cool down. So the reason why to explain the DB gap, there are some scenarios. The spectral evolution, which was that if you have a trace amount of hydrogen mixed in the helium atmosphere white dwarf, as it cools, the hydrogen is going to float up, and then eventually it will look like although it's mostly helium-dominated atmosphere, it will look like it's a DA for a short while before the convection mixes it all in and will look like a DB again. So that's called spectral evolution theory, and there is a calculation how much hydrogen you need to be able to do this, and some studies of the atmosphere suggest that it seems like this is something that might be contributing to the DB gap. The other one is we know for sure is interacting binary white dwarf stars, two white dwarf stars with extreme mass ratio, transferring helium from the mass donor is the lighter white dwarf because the degenerate material, the lighter star is bigger. So that's the one that fills a Roche lobe and transfers the material. And the spectra shows that the transferring material is helium. So when it finishes all that, it will eventually be a 1 helium atmosphere white dwarf star. And the system temperature of AM Canven system, the International Binary White Dwarf systems, are about 30,000 degrees, around the temperature that we start seeing the dBs. So that's one channel we know that it's going to produce a dB. So maybe those are some of the dominant way to make the dBs. And the interacting binary, the binary method wouldn't, they're not coming from that. Those are just coming in from the outside, from the hot end to the cool end. So maybe that might be more of a dominant way of making it. So there's some other scenarios there, but so let's find out. Now that we have dBs in the dB gap, we thought that we had this nailed with the first two scenarios that I just mentioned, but now that we have them, shouldn't we take a look at them? So, and then in the UV, because if you have a trace amount of hydrogen, it will much easier to show up. Also, any metals and anything else, it'll show up in the UV much better. So we went and asked for time and got some time. So here is the dBs that we see in this temperature range from 30,000 to up. The blue ones are the ones that we know that's pulsating. So the one from the leftmost blue to the higher up you can consider it as the dBs in the gap. So we got time for 2 objects. If I was a queen of the universe, I would have given myself time for all of them, but that didn't happen. So we have 2 objects. Let's see. Yeah. And okay. Here's a spectrum. And so we're not completely done with it. And so we do see helium-2 lines. So definitely it is. We might have metals, but we don't know that for sure without like all the other things cleaned up. So we'll have to wait for a bit. And we also are going to go after the right at the edge of what we call it the hottest end, which is called blue edge of the instability strip, to see if they're also pulsator, which we can also see much better in the UV because of the geometric cancellation and limb darkening will favor the amplitude of the pulsation modes to be higher in the UV. So that's what we're doing. And we got some data, but not all. The next data should be coming in next year. And again, it's preliminary. We seem to see some metals, but we will let you know for sure maybe next year when we got this all sorted out. But yeah, okay, I probably used more than my time. Thank you.
Oh, this. Ladies, gentlemen, questions? Any questions online?
It's a perfect talk, yeah.
Clearly.
Thank you.
Alrighty, let's thank the speaker again. And let me invite Dr. Barrett. We're switching gears from white dwarfs to neutron stars.
Good afternoon. My talk is about actually white dwarfs. This is an object called AR-SCO. It's called a white dwarf pulsar. That's the way it was. And I'll explain why that's the case. AR-SCO is a magnetic cataclysmic variable. It was discovered by Marsh in 2016, distance of 117 parsecs, fairly nearby. And it's composed of a white dwarf and a red dwarf. And of course, the white dwarf is accreting from the red dwarf through Roche lobe overflow. It's a fairly rapidly rotating white dwarf. The period is 117 seconds, and it's in an orbital period of 3.56 hours. And it has a known spin down period. The luminosity is fairly high, 2 × 10^32. So which button do I push? we go. So because of that, it was proposed that the luminosity was caused by the spin down, is due to the spin down power, hence a white dwarf pulsar, okay? But one of the implications of that model or scenario is that you require quite a large magnetic field at the white dwarf, basically roughly 500 megagauss, okay? And that means that the magnetic field at the companion is 160 Gauss, all right? A similar system is AE Aquarius. It has a spin period of 33 seconds. And that model, that scenario is called a magnetic propeller, where the material accreting from the donor star, as the white dwarf is spinning around, it actually picks up and throws the material out of the system, okay, hence the propeller. That's a much lower magnetic field, probably around 1 megagauss at the white dwarf and 1 Gauss at the companion, okay? So over here on the right-hand side, I show some modeling of AR-SCO that people have done. And the big curve here is the synchrotron model that they give. This is a single component model. And then the lower one here, they actually give a 2-component model. This here is inverse, synchrotron inverse Compton here, okay? But they're basically related. You'll notice there are some missing gaps here in terms of data, all right? This is the early archive data from Marsh. So at this point here, just to give you some idea, this here is radio emission. And then what we're trying to do is actually get radio data at higher frequencies to fill in this gap, all right? So we did do that. Is that right? So we wanted to fill in the gap between 12 and 500 gigahertz to measure the spectral index, all right? To actually find out what's going on with the synchrotron emission. We got some time on the submillimeter array on Mauna Kea. We got a 1-hour observation at 210 gigahertz, and then we got another observation at 345 gigahertz. In the 200 gigahertz observation, we were able to get a periodogram, and we find a period, as you can see here, at about twice the spin period. This could also be the beat period. Okay, and the amplitude of that is about 7%, okay? So if we go off here and actually look at the actual data, this is the SMA data. This is 210, that's 345 gigahertz. And this point down here is VLA, and that's 22 gigahertz, all right? So by fitting this new data, we get a different type of spectrum. We actually find that the synchrotron emission actually turns over. So synchrotron emission models, kind of standard models, are defined by 3 frequencies: the injection frequency and energy injection frequency. That typically gives you 1 curve. Okay, 1 break in the curve. You've got the cooling frequency, that can be up here. And then there's another break in the frequency, and that's the self-absorption frequency, all right? And that's kind of an important frequency because the self-absorption frequency drops off very quickly. And it's also very strongly dependent on the magnetic field, okay, of the ambient plasma. So based on this model, my fitting of the data, there's 2 models. The solid blue line is what they call the slow cooling model. The dashed line is the fast cooling model. I tend to prefer the slow cooling model, but you might argue that both of them kind of work, all right? Anyway, the slow cooling model gives you an ambient field of 1 Gauss, all right, which implies that the magnetic field of the white dwarf is around 3 megagauss. It's a weak field system, all right? The importance of this is that for AR-SCO is that if you have a 500 megagauss field, how do you get that magnetic field? Because if it was originally there, there's no way that you could spin up the white dwarf to 117 seconds, all right? So the field initially for the white dwarf had to be a low magnetic field. You spun up the white dwarf, and then after that, there's a mechanism, some mechanism actually amplified the field. One of those is white dwarf crystallization. There's models that say you can actually. The other is that the white, it's just a low field white dwarf, and it's a standard scenario. So that's kind of the result of this, is that at least these radio observations of mine imply that there is no white dwarf crystallization, and the white dwarf has a weak magnetic moment. So here's my conclusions. I pretty much covered much of that. As I said, my belief is that because it has a weak magnetic field, the white dwarf, that this is also a magnetic propeller like AE Aquarius. There are two other systems. When I wrote this paper, there were only 3 known systems that had synchrotron emission: AE Aquarius, AR SCO, and J1912-44. There's now a 4th system, but they are very rare, and they're really very interesting systems. Thank you.
There we go.
Paul, I take issue with you calling it a cataclysmic variable and Roche lobe filling, because there's absolutely no indication of mass transfer from the system at all. The other issue I'd like to ask you to explain to me is how this system shows spin-pulsed linear polarization reaching 40%. If it's only a weak field MCV, why have not any of the other ones showed this bizarre behavior, which has been attributed by ourselves and others as being the, a magnetic dipole rotating? I just don't buy it. Sorry.
I don't know what to say about that. I mean, to trying to fit the synchrotron spectrum, I can't fit it with a high magnetic field. So it just, that's not possible. Either that, you can't do it. I should say I can't fit it with a simple synchrotron emission model. It would need to be a much more complex synchrotron emission model. It could well be. There are potential tests to do this. If it's a low magnetic field, then the emission region should be quite large, about the size of the binary. And if it's a high field, then it should be very compact. And there's a possibility one could do VLBI and actually resolve the emission.
VLBI has been done, but the emission has just been resolved to something like the co-rotation radius. So that's several times the separation.
Yes, I know, but that's at 22 gigahertz. You're going to have to do it at 210 gigahertz. You're going to have to basically use much higher frequencies. EHT would do it,
Any other questions or comments? Let me jump in then. So when you were comparing the fast and the slow models, what drives which one would be more appropriate?
It's basically the as I said, it's the cooling frequency and the injection frequency, energy, the injection of the electrons. And that's just based on the magnetic field and what you believe that the electron energy is in the system, okay? I mean, these models are typically used for gamma ray bursts, for modeling gamma ray bursts. And, you're just deriving the parameters of the ambient medium.
All right. Let's thank the speaker again. And let's invite Dr. Yang to the stage.
Okay, good afternoon, everyone. Thank you very much for having me here to give a talk about the orbital variation of the galactic pulsar for U-1907. And these are my collaborators from MIT. So the galactic pulsar for Ulithi 07 is located near the galactic plane. Okay, thank you. And so this is a galactic plane, and this is a location of the pulsar. And this pulsar is one of the 35 high mass accelerations with the long high magnetic field. And we are using the X-ray telescope to probe its spectrum and light curve variations and different orbital phase. So we are using Chandra, which covers the soft energy band, and a new star in the hard X-ray energy band. And here is a cartoon shows the pulsar system. And this is a pulsar with a spin period about 440 seconds. And this barrier system interacts through the accreting through a stellar wind, and it has a 08 light supergiant as a massive companion. So this barrier system is has a 8.37 days orbital period. Here we have one new star observations is about 78 kiloseconds, and 4 Chandra observations. So all the 4 X-ray observations was taken in one single orbital period. And here these 4 Chandra observations are shown in yellow, green, blue, and purple. And here this is taken when the pulsar and the periastron, and a new star is taken and a periastron. So in total, we have 140 kiloseconds Chandra observations. And the outside, the light curve is taken from decades of the RXT observations. So separately, we have plot each of the Chandra observations, the light curve in this figure. And we can say, and periastron, if we recall the back, this Chandra, when it is closest to the massive companion, the light curve shows some zero counter rate, shows some dips, which means there are some dense material is between the pulsar and its companion blocked the photon counts. So next, we have plotted the hardness ratio to see if there's any other variabilities. And the hardness ratio first, it is calculated by the photon counts in the intermediate energy band 2.5 to 4.5 keV divided by the count rate between 0.5 to 2.5 keV. Still, these are the 4 Chandra observations and different orbital phase and periastron, pre and post periastron. So we can say there are lots of variabilities with regarding the change of the hardness ratio and also some zero dips. So the hardness ratio is mostly between 5 and 10. And then we also plotted the hardness ratio in the hard energy band, which is calculated by the counter rate between 4.5 to 8 keV divided by the counter rate between 2.5 to 4.5 keV. Similarly, even the periastron, it shows lots of variabilities. So overall, the hardness ratio is smaller than the hardness ratio in the soft energy band. So far we checked their light curves. How about the spectrum? Then we fit the spectrum of each of the Chandra observations and different orbital phase to see if there's any changes and different orbital phase. First, we fit the overall with the power law, and we also included the partial covering fraction function, and as well as the SM green absorption model. And especially we added the ion K alpha line. And here we fit each of the Chandra spectrum, and later we have also extend the spectral fitting to the hard energy band with the new star. So this new star spectra, we use the parallel model to fit the overall model to see if it will be consistent with the soft energy band, especially at the higher X-ray energy end. So there are extra absorption around 12.2 keV. So in the residual, which is due to the higher cut models and the cut-off energy and 12.2 keV. So we have put all the spectrum from the 5 different orbital phase, the 4 Chandra observations, and 1 new star observations and apastron, and especially we can see and periastron. The ion K alpha emission lines, it shows the minimal value, and the periastron, especially at the new star, it reaches the maximum. It indicates there are clumps in the wind. So for the hydrogen column density, it also shows smaller minimal and periastron, pre and post periastron, but it reaches maximal and the opastron when the pulsar is further away from the massive companion. So then we put all the Chandra high resolution X-ray spectroscopy together to see the emission line. And these are the wavelengths, and this is flux from the high resolution X-ray spectroscopy. We can see the clear ion K alpha emission lines, as well as the K alpha lines and the silicon. It's argon and silicon, but there's low significant no features and the magnesium. So this ion K alpha lines indicates the cool and dense clumps in the stellar wind. So overall, we have put 140 kiloseconds new star and 140 kiloseconds Chandra and 78 kiloseconds new star and different orbital phase to see the variabilities of the flux and brightness and also the absorption column. We can say meaning zero flux and the periastron because of ultra dense material. And also ion K alpha Florence line shows different forms of clumps in the wind. Especially we see the variabilities of the due to the severe wind clumps in the innermost companion. Also, it depends on the radius of the stellar position. And also there are dense clumps within 1.5 radius of the massive companion. Thank you. I would like to take questions.
So before I open the floor to questions, may I ask Dr. Valio to go mic herself up? Okay, they have to mic you up. And may I ask you, please, Dr. Yang, to answer questions on that? Okay, questions, comments, please.
No one saw that. It's not broken yet.
Let me maybe open the floor with the first question. So obviously you see the clumping happening from the 5 data points that you have. If you were to reobserve, do you think the clumps have a temporal component to them? So do they change in time?
I think if we observe again and the periastron, when the person is close to the massive companion, there will be clumps. Since it's changing over time, the stellar wind, but it will not be exactly the same, but still show many variabilities. And we can still clearly see the dense clumps from the light curve and also the spectral fading based on ion K alpha line. Yeah.
Do you think that we could learn something from looking at different clumping as time goes on?
Yeah, we can, especially using the modeling because the time limit I didn't show, we can see many features and occurring and how even, yeah, the more interactions from the modeling part. Yeah, especially different radius between the person and the massive companion. Yeah, yeah, thank you.
All right, any other questions? Yeah.
Hi, Jude. Nice talk. So my question is there any evidence of infall in the system? You have clumps orbiting at a couple of stellar radii. Any evidence that this is coming down on the neutron star and causing pulsation, not even pulsation, accretion emission?
So what's your exact question? So say any
Associated with, do you see any flaring with associated with material falling onto the pulsar?
And the flaring, which kind of flaring do you mean?
Material should, if material's in orbit, some fraction of this should fall in.
Mm-hmm.
Do you see any evidence of material impacting the surface of the pulsar?
From the modeling, we see like if when there's a dense, if it's smooth, there's not much material falling to the surface of the neutron star. But when it's there was a strong wind, like it's not smoothing. Yes, there is. Yeah, so I can show you like one more slide. Oh, it's not here about the modeling. Yeah, thank you.
All right, let's thank the speaker again.
Thank you.
And from pulsars to exoplanets, Dr. Valio, the floor is yours.
Okay. First of all, I'd like to thank the organizers for giving me the opportunity to speak here. And I want to say that I feel like a pop star with like this mic. Well, switching gears, star spots from solar-like stars. And here are the co-authors. And I'd like to point out that Shelley Zaleski led most of the work. So, I guess. Okay, so star spots, we know that sunspots are the dark regions on the surface of the sun, and they're dark because they're cooler due to an enhanced magnetic field. And we know that all convective stars also exhibit spots on their surface. But of course, I mean, using techniques to identify and measure, let's say, the presence of these star spots and the magnetic fields, that's the Zeeman Doppler imaging. It only works for fast stars. So how do we go about doing it for other stars? And here, that's where I come in, and we take advantage of the high resolution or high photometry resolution of space missions like Corot, Kepler, and TESS, which I'm going to tell you about a technique that I developed 20 years ago called transit smart mapping. And that's basically, when a planet transits, it may occult a spot on the surface of the star. And when it does that, because the spot is darker than the rest of the photosphere, you will see a bump in the transit light curve. And you can model this bump and get information about the physical characteristics of the spots, such as size, temperature, or intensity, and its position. And you can measure things like differential rotation, etc. And just to point out, the model here is a simulation with a 2D pixelated image of the star with limb brightening. Okay, so, but that example that I showed you was for like a hot Jupiter transiting in front of a star, a solar-like star, and we don't see any structure in the spot. However, if we have a small enough probe that is a terrestrial-sized planet, we might start to see structure on the spot, such as umbra, which is the darker part of sunspots, and penumbra, which is the surrounding, a little bit lighter region with a less strong magnetic field. So what we did was, in order to prove if we could detect those, here is active region 2192 on October 214. It's a fairly large active region with lots of spots with different umbra and penumbra. And so we made simulations across 3 different latitudes with a planet the size of Earth, so one Earth-sized planet. And this is what we obtain for the sun, right? I mean, if we had the transit of a Earth-sized planet, and you can start to see the structure of the umbra, and then the penumbras are the shoulders here. Okay, and so now we went ahead and did, and for these, what we got from the umbra penumbra, is that the ratio of the flux from the umbra and the penumbra varies between 2 to 4 times. So the umbra is 2 to 4 times darker, or its flux, it's stronger than what comes out of the penumbra. Okay, so now what we did was we went ahead and modeled. So we used these, applied that eclipse model that I just showed you to these features here on the light curves, and to see what we would get out. And well, here are the numbers, the spots, radius, intensity, and longitude, and each spot, well, we looked at it for an umbra and a penumbra component. And this is the reconstructed image. If we just forget about this and just model this using the eclipse model, and we think we got a pretty good match. Now, life is not always as easy. And of course, if we want to try and detect this in real data, because what we're looking here is noise from the sun, which is a fairly close by star. But if we start to look at other data, like for instance on for Kepler data, we run into noise, and this is not something that we can get rid of, because beside just the instrumental noise, we also have stellar pulsations, the P modes and the convection that is just intrinsic to stars. So how do we try to estimate, well, I don't think we'll be able to see it on Kepler data, because of course we need a small planet, which means shallow transits, which reflects to strong, higher noise, right? I mean, and here is just the random noise for the satellite. But what about Plato, which is the next satellite for looking at transits of exoplanets? So we use the calculations from Morris et al. To try and estimate what all these P mode oscillations plus the photo and the random noise estimated for the Plato satellite is like. And here are just the 3 examples of what we got. So here are stars of different sizes. So this is a dwarf, an M dwarf, 0.3 sun. Here is a K star, 0.7, and one solar radius. And the magnitude of the stars are different. So this is a dimmer one, magnitude 15, 12, and 11. And also what we varied, these are all the simulations for a 3 Earth-based, the Earth radii planet. And then here's the penumbra intensity with respect to the center. So the center of the star is 1, and here's the penumbra. And all the umbra had 0.55. And what we found was that this is the size of the spot, 50,000 kilometers, 50,000 kilometers. We would be able to detect the penumbra would be this shoulder that you're looking here, just above the 3 sigma noise level. So my conclusions is we might be able to detect the structure of penumbras in star spots that separate the umbra from the penumbra, but we need a small enough planet, such as a terrestrial planet, which can be, for instance, 3 or 2 Earth radii. But the important thing is that we have to take into account the noise, not only the instrumental noise, but also noise from the P mode oscillations on the surface of the stars, which makes our life harder. But it is possible, for instance, for these combinations of parameters. I'm not going to read them out. You can read them for yourself. And so hopefully high precision missions like Plato will be able to observe, and we might be able to distinguish between umbra and penumbra. Thank you, and I'll take some questions now.
We have some time for questions.
Hi. Hello. Thank you very much for that talk. I think this sounds like a very fascinating idea. And it's
where are you?
Oh, hello. Back here.
Okay. Hi.
Hello. It sort of got me wondering, so assuming that these stars that we're looking at are anything like the sun, where we have these migratory sunspots that change depending on where they are in the solar cycle, could we potentially get that sort of information from these other stars, or is that way too much of a stretch?
Well, it depends on what kind of system we have, right? Because the transit only occur at one latitude, unless it's in the polar orbit, like we model Kepler-63, which is in the polar orbit. Or we can have like the system Kepler-411, which has 3 transiting mini Neptunes. So then we can get information, yes, on what the spots are like. And like Kepler-210, which has one planet that transits parallel to the equator, and then the other one, which is in the inclined orbit. And we were able to infer that above, I think it was like maybe 40, 50 degrees in latitude, there were no more spots. So then we were able, I mean, of course, to get like a change in cycle, we need to observe it for years. I mean, Kepler observed some of the stars for up to 4 years. So if you're lucky enough, you can get a multi-planet system or a planet in an inclined orbit. And yes, you might want to see that. And those 3 planets that I cited, I mean, if you look under value, they're all published in APJ.
Fascinating. Thank you very much.
Thank you.
Thank you. Let me close this for the questions because we're out of our time, but let's thank the speaker again, please. And let me invite Dr. Hambleton to talk about astroseismology.
Hello, everyone. Thank you all for sticking around so late in the day. So today I am going to be talking to you about the astroseismology of red giant stars and what binary stars have to say about them. So I don't need to explain too much about astroseismology. We've had a few talks today, and I'm sure most of you are aware. Astroseismology is the study of stellar oscillations to really understand the interiors of stars. So by studying the pressure modes or the G modes, where the restoring force is buoyancy, we can really learn about, say, the internal structure of stars, the pressure, the log G, the internal rotation of stars, the masses, radii, and so on. And so we have pulsating stars across the HR diagram. Here you can see that there are all kinds of pulsating stars, and I also have light curves here to show you how differently they can be represented just as a function of time when we're just looking at their light. And so today I am going to be focusing on these guys here. So those are the solar-like oscillators and their evolved companions. So solar-like oscillators have a very distinctive power spectrum. Here you can see the characteristic peaks where you have a couple of very important global parameters. Here we have what we call nu max, which is the frequency of maximum power. And also here you can see, so we have frequency and power. You have the separation between pulsation modes that have the same number of nodal lines along the surface, and this is known as the large frequency separation. And so this is a very characteristic frequency diagram for solar-like oscillators. And one of the really cool things is that even by just looking at several power spectra for different objects, so these are power spectra for objects on the main sequence, and then here we have subgiants, and then the lower red giant branch. You can see here the frequency of maximum power is decreasing, and again it's rescaled here, so again decreasing as we become more evolved. So more evolved stars have a frequency of maximum power that is at lower frequency. And then in 1995, following several works, Kelston and Bedding actually created in a nice package the astroseismic scaling relations, which relate these two global parameters, these two oscillation parameters, to the radius and the mass of the soul-like oscillator. And so if we take these two parameters, the frequency of maximum power and the large separation, and also the effective temperature of the star, and then we relate it to the sun. So we're using the sun here for calibration. So in relation to those values for the sun, we can determine the masses and radii for thousands of soul-like oscillators. And here you can see the effective temperature and the large frequency separation. And these are just thousands of stars, main sequence stars, and red giants for which the masses and radii have been determined using the scaling relations. And so, of course, we then have to test how well we're doing with these scaling relations. And so in 2016, GALM identified 10 red giant pulsators that were in eclipsing binary stars. And so using these objects, you can extract the masses and radii from astroseismology by just studying the pulsations of the giants, but you can also extract the masses and radii by studying the binary systems, by looking at the eclipses and the radial velocities. So here are the 10 different systems, and you can see in black you have the light curve and the models in red for the eclipses, and then you have the radial velocities. And so by modeling these 10 objects, they were able to compare astroseismology and binary star results. And so what did they find? They actually found that there was an offset in both the mass and the radius between astroseismology and binary star results. So here, dynamical radius is the radius that we get from binarity. Astroseismic radius is the radius we get from astroseismology, and the same for mass. And so they showed a discrepancy that was about 5% in radius and somewhere between 10 and 15% in mass. However, then we went a step further, and some groups decided to test those tests. So then we have one system, which is a Kepler system, and we had two other teams that went and modeled the same system using the same modeling program, JKT-EBOP, and they published their results. And if you compare their results, here we have the mass and the radius, and each box represents the 1 sigma uncertainties, or the 1 sigma box around the results. Oops. And you can see that while they agree in mass, there's some discrepancy in the radii of the results shown. And so if we look at the models, you can see they're quite discrepant, even if you just compare the models. And then if you also compare using different modeling programs, you can see these are the same results for two different modeling programs, JKT-EBOP and Phoebe. And you can see that the models are very different. And so you also have to be careful in which modeling program you're using. So in order to make sure we're doing a good job, I have modeled 2 objects now. And here are some of the results. And you can see I've incorporated Gaussian processes and also Phoebe, which is an advanced modeling software that uses the Roche model rather than just triaxial spheroids. So here are 2 objects. And so how do they compare with those results of GALM and the others? So the results from my models are in red, and so we still are finding the same discrepancies as we were before. However, all is not lost, because if we, instead of using the sun for a calibrator, try maybe using one of these objects that we have good results for. So instead of calibrating the astroseismic scaling relations with the sun, we calibrate the astroseismic scaling relations for red giants using a red giant. So by doing that, these are only preliminary results, but you can see for mass, radius, and log G, we can already start to see an improvement in the astroseismic scaling relations for red giants. And so here are my conclusions. I just want to say that while binary stars highlighted a discrepancy, we can also use binary stars to improve the scaling relations. There still work needs to be done. We need to improve our calibrators. We need to make sure that we're consistent within the binary star community as well. And we need to make sure that we also have good observations, good radio velocities, and continue this work. Okay, thank you.
Questions, comments? Should I start running to urine or?
Well, thank you, Kelly. This is very interesting. A beautiful talk. In scaling relations, there are these correction factors that people apply. So I wonder, I can't remember whether GOM actually included these correction factors. And so I wonder whether you would comment about how that could affect the results of these comparisons.
So there are all different kinds of correction factors, right? There are correction factors where you change the powers. There are correction factors where you include a metallicity term. There are correction factors where you just use a different value of the large separation for the sun, for example. I slightly tweak this. I'm just showing an alternative approach where maybe you just use a different star as a calibrator, because of course in phase space, in the modeling space, then you're closer to the red giant object. So if you can really pin down, I understand we're never going to get it as precise as the sun for one of these objects, but if you can maybe have some other calibrators that are closer in phase space to those red giants, then maybe that we can do a better job for all the red giants.
Right, and so that effectively means correction factors of one.
Exactly.
If you choose the right reference.
Exactly.
Yes, okay. Thank you.
Any other questions?
So I think it makes a lot of sense to calibrate it to red giants. But why would we calibrate it on one? Would it not be better to calibrate it on an ensemble of red giants?
Absolutely. So this is just preliminary work, and actually the objects that I have chosen, I selected because they are more difficult and they're more likely to be discrepant with the other binary star results that we've seen. And so they're the badly behaved objects. I think Kepler has 10 good objects, maybe actually 13. And so maybe looking at all of them, but maybe the better behaved objects especially might give us better results.
Hi, Kelly. Very nice talk. So I have a question. In addition to for the calibration, in addition to the mass and the radius, whether it's possible to introduce another parameter like the core mass of the red giant branch star, whether that could help or not? I'm not so.
Right now, the scaling relations provide you information about the mass and radius, and also the log G and the internal density. So those are the 4 parameters that I'm looking at that I can extract from the binary star physics, and I can also extract from the scaling relations, and those allow me to really calibrate the relations.
All right, let's join me in thanking Kelly again. And one more time for all the speakers in this session. All right, now I'd like to invite Mariam back up to kickstart our last part of this session. So right now we ask you for what Division G can do for you in the next triennium. So please do not hesitate to let us know what possible actions the division could take. Is it sharing of information? Is it sharing access to the data, to observing facilities, trying to come up with a more global plan on how to tackle some of the standing problems in stellar astrophysics. So I'd like to ask whether there are any pieces of advice that you can dispense so that we can do a better job serving you as a community. I'm going to be running back and forth if anybody wants to open this. And my suggestion is that you use that mic for any comments.
Okay, thank you very much for the opportunity. I'm a new member of IAU in Division G, and obviously, as a young and upcoming researcher, we need collaboration among the division groups. So how can you assist in working together, like collaboration, and then accessing data? Because we are still starting astroseismology as a field. So how can we work together? And then when it comes to publications, usually when we submit, obviously in the morning session, someone asked, like, there are some journals that ask you to pay in order to publish. And then how can we alleviate those type of challenges?
So this is a really good question. So that's why we will host a webinar that we will do quarterly webinars for Division G. And we will invite a lot of people from stellar physics to join a webinar. We will invite the first, the very known astronomers and all the people from our Division G. We will join and we can discuss and share our data, our all about open science and our knowledge and what I think it will be great for the new people and for young people in our Division G. This is idea, and there is also newsletter, which would be also a quarterly newsletter for Division G. And also we can you can participate, of course, to the IAU symposia to share our work and our results. So anyway, you can also to send me email if you want to have a name of some collaborators. Maybe I can help, and other people also from our steering committee can help also. So we will really to improve communication to raise awareness of our knowledge and our results.
Let me also add to that, if you're comfortable with Slack, Division G has a public Slack channel. So you can join a Slack workspace. So you can join that workspace and carry the conversation with people. So if it's astroseismology you're interested in, there's an astroseismology channel there that you can join and then reach out to people who are on the channel who are doing those things. There is an official Division G IAU Slack workspace. I have to look up the address, but let me look it up while I pass this on to Göran, and then I'll share it in front of everyone.
Yeah, thank you, Andrea. Maybe a lot of younger people like WhatsApp or Instagram. I don't know. So because let's see, we can see how we can manage that. Yes, please.
Thank you. Maybe that's my lack of knowledge, but I looked up the Division G website on the IAU webpage, and like the last newsletter is from 2021 or so. So I think what you need to get this is at least have some link on the IAU website to where the current material is. And maybe I'm not young enough anymore, but I wouldn't want to have like a Instagram page or something. Even the Slack channel, it's a nice idea, but at some point, I don't know, I'm in 20 workspaces on Slack, so it just gets overwhelming. at some point. So having something on a website with a newsletter that informs you every 3 months or so is probably good enough to see what's generally going on. And then people who want to interact on a specific topic should maybe find their individual platforms.
Yes, thank you.
In addition to that, one thing that I think might be nice as a division is to give also a bit of an overview of the different sub-commissions and working groups, so that especially people who are new to the division can get a better idea of the whole range of stuff that's going on.
Okay, thank you very much. We will do our best to improve communication and to start a really quarterly newsletter for Division G. And we'll try also to open a list for Instagram or WhatsApp or something like more easy for younger people. Thank you very much.
So for those of you interested in Slack, it's iau-divg.slack.com. So you can join that immediately. Speaking of the website updates, the issue has been that we've been told really month after month rather than year after year that the IAU web pages will be undergoing major revision. This is what's happening right now, but we've constantly been pending with material that's already prepared to put on there, but they told us, don't do it now, wait until the new system is ready, and that's when that happens. And of course, the timescales of these changes are roughly nuclear. So that's the unfortunate reality that we're living in.
Well, if I might just comment on this last point, as a Danish representative who has to go to all these boring bureaucratic meetings, the new IAU web pages are being set up because ESO decided they could no longer support the web pages, and they should be up and running on a fairly short nuclear timescale, like the start of next year. I don't know what happens on a nuclear timescale of 6 months, but it's pretty dramatic, I'm sure. What I want to get back to as a very, very old IAU member, more than 50 years, long before Division G was started, is a completely different issue from the ones we've been talking about here, namely the detailed modeling of stars. And the fact that we all run MESA models or something else, but I think there's a lot of work needed to make sure that these models are actually accurate representatives of the physics, and that the physics we include in the models is as good as possible. And that's something that we are each doing individually, but I wonder whether Division G, and especially the stellar evolution part of Division G, could help circulating the idea that we have to be very careful about this modeling. We can't all just run MESA as a black box and trust the results coming out of that. We need to compare different evolution codes. Of course, we need to compare the results in detail with observations and try to understand why and when the models don't match the observations. That's something that's been going on for, I wouldn't say centuries, but at least many decades. And we're not there at all yet. And one of the things we need to do in that connection is also to go a bit beyond this division, or maybe include the Sun as a member of Division G, because after all, this is also a star, and this is a star that we know pretty well. And we use that as a benchmark to testing our models of stars. So I think this interaction between the solar interior studies, I'm not talking about the solar surface studies, of course, but solar interior studies and the stellar studies are very important, and something that we might, as a division, try to keep at the forefront of our attention. How we do that, I don't know. I'm too old to start new things, but I think this could be important and useful.
I think, thank you very much for your suggestion. I think the first of all, we have to improve our page web in for our Division G. And we can see from that if we can include some models or something like this in our page, no? I will try to do that with the Secretariat of IAU. I have tomorrow meeting with the Secretariat. I can discuss with the Secretariat about that. It's really a very great idea. Other idea, maybe we can do a big list of emails for all the people from Division G, and we can connect with each other by emails too.
So the Secretariat does not want us to do that. They want the keepers of emails to be private. So all communication needs to go through the Secretariat.
Maybe just a web page web.
Right. And I actually think it's a good idea because some people can abuse the email list otherwise. Maybe a thought on this. To me, this sounds like a perfect case for an interdivision working group. So if we established an interdivision working group that was tasked to do precisely what you proposed to do, this would allow people from different scopes of the IAU to join and do precisely this. So my suggestion really is to possibly try to act on this early so that we can establish a working group, or at least propose a working group, see how many people will join it, and then establish it with a clear directive of what to do.
Okay.
Other thoughts and comments?
Maybe I have just an idea now. Maybe we can meet also one year to do, like we can do a meeting about Division G meeting 1 year to discuss our results on our about our models, about open science, and for also it will be great for young people. And maybe I will ask tomorrow Secretary if they can organize for us this meeting for each year, maybe in December or something like this. That would be great to meet each other in person, and we discuss our result, and maybe we can do also proceeding about that after. No? This is some idea like this.
I think a virtual may be easier.
Virtual is a webinar. Webinar, it should be one quarterly, yeah. But for the meeting in person, maybe it could be each year. We can meet all together in December or something like this to discuss about science. Yes, please.
So I've organized or been part of the organization for the Cool Stars meetings, which are centered out of Cambridge, but are worldwide at this point for a couple of years. And I was thinking almost exactly of this last thing because we did a totally virtual meeting at one point, and now we're doing these mixed meetings. The virtual meetings, once you get in the rhythm of them, are fairly easy to set up and allow scientific discourse without the commitment of an actual formal meeting. One of the problems with the formal meetings is they require a large commitment. There's a huge schedule of them already. I mean, all the way out for the next 3 years, we kind of know what the schedule is. So I think creating a new meeting that's physical is going to be challenging.
Oh, yeah.
But I think a seminar series where maybe it's one day every 3 months, one day every 6 months, where you have something you want to present and you get people in a rhythm of, the first Friday of the third month of the year, every third month, we do this. It's stable and it's regular. That could work and allows the Slack channel to be real communication. And so I was thinking exactly the opposite, make it virtual, because physical commitments are going to get harder and harder as time goes forward. We see that already. This meeting is a big example of the drop-off in physical participation that we're going to see in the future. But a sort of seminar series, which isn't one person, which is 4, 5, 6 quick talks, and then let's chat about the subject, I think is something we could do.
Okay, thank you very much. So let's start first with a regular webinar, okay? A regular quarterly webinar, okay? And let's see.
What else? Yeah.
I want to ask one question about the proceeding. How does it work? The IAU proceedings for Division G.
For this moment, we would like to start a Division G newsletter about the proceeding. If you do a really meeting each year, we can do proceeding and we can ask help to IAU Secretariat. But let's see.
Ultimately, I think the only reasonable thing or practical thing would be that whoever's presenting writes an extended summary of sorts that goes into an electronic only kind of bulletin that is then archived on the division webpage.
Oh, yeah, for proceeding. It's like IAU symposia proceeding. It will be something like that.
But I imagine it's less involved because you do not want to burden people with writing elaborate proceedings for this. Anything else?
Anyway, if you have any idea or any suggestion, please contact me. And we will try to do our best to improve our communication.
So we still have 8 minutes, and you have a president listening. So now's your chance.
This is maybe more as a young astronomer. I found it really difficult to understand what the main goals and questions that the division is trying to answer. And I think this is kind of the thing suggested initially about a working group with the solar community is to like, what are the main questions of each of the working groups and stuff, and how does the research presented here in the past 2 days fit into those questions? Yeah, and I think maybe that's, what are they? What is the main direction to go in as a division? Yeah, this is an open question.
Yeah, this is open question already. So we will study really the strategy to do it, and we will want really to have time to study the strategy about that. But I note it.
So maybe my take on this is that individual commissions within the division are the direct science liaisons, whereas the division, which comprises all the commission presidents and some at-large members, I see primarily as communication facilitator, which means we do want science highlights, but the goals that I see foremost is to enable communication across the global world. So instead of having small little islands that may be doing the same thing unaware, to essentially be able to provide a medium of communication between them. And then thinking maybe a little bit more adventurously to push forward the science that we represent. So everything stars and stellar physics, if we can prop it up in any shape or form, either through helping organize symposia or focus meetings or anything that's happening that would promote the science. This is where you as members turn to us as officers, and we bounce ideas. We try to guide you to write a strong proposal that would then be accepted as a symposium or a focus meeting. So I think in terms of that, also some parts of the world have tougher access to either observing facilities or data. And we're there to jump in and try to put you in contact with some of the observers or with some of the facilities, or provide you with data as best as we can.
Sorry to come back, but it occurs to me that one thing and I say that as a former commission president and division president, the commission structure has been very little visible at this meeting. And really also in the communication, the commissions don't really appear very strongly. So that's maybe something to keep in mind, because after all, the commissions are where the more detailed work could be done, specific to certain areas, like pulsating stars as one example. And so if there are issues specific to that, it should be more visible also in the work of the division. And that's something that maybe one could take up in the next triennium to see how the commissions. I don't even know who's president of the commission for pulsating stars, which is very embarrassing for me, but that's the way it is.
Or even working groups as well, because those take the individual problems. Yeah.
Yeah.
So the issue always remains that we are temporally constrained. Not yesterday, on Friday, I tried to give an overview of Division G and what's going on and present the officers, but of course, it's the first thing, and memory is, free fall time scale rather than nuclear. 4 more minutes, food for thought. What can Mariam and her team do for you?
Okay, Kelly.
So one thing that was a little bit sad for me about this meeting was that there wasn't much stellar activity. There's not much about stellar science in this meeting. And for the next meeting, I really hope that that would change. And I just wonder if you can comment on what we as a community can do to make the next IAU General Assembly something that's interesting to stellar astronomers as well.
Okay, something like a business station or politics sessions. Okay.
Organizing symposiums, like how can we get involved? How can we work together to make the next IAU more exciting for stellar?
Yeah, but that maybe we can discuss this during the regular webinars together. It will be great, yeah.
And maybe emails when it's time for preparing for symposia.
Yeah. Maybe we can invite astronomer, especially about this subject, how we can prepare IAU symposia and during webinar, and we can discuss that during all day. Okay.
I have some ideas. I would like a symposium on pulsating stars and binaries. I know some of you are interested in that stuff, and I'd certainly like to discuss it with people who are interested. So yeah, let's do that.
Yeah, it should be very good. Maybe we can also to have a special session during future general assembly just to discuss about business and the politic sessions about Division G or something like this.
Maybe let's call it something more exciting than business, though.
Yeah, a politic, no, a strategy. Yeah, something like strategy and challenge.
Last call for questions and comments.
There is here a question. All right. So sorry.
So to follow up on that, I was wondering, were there no proposals from our division, or have they not been selected for this IAU specifically?
We did have several proposals, but as it always happens, we get them a day before the deadline. So we cannot provide any insightful feedback, and they were not competitive enough. So when they say September 15th as the deadline for letters of intent, they mean it, because then we get it. We work with you to make the symposium proposal as strong as possible. And then the December 1st deadline does not hit you unawares, but we have actually gone through iterations and we've made your proposal strong, because we see scores of proposals every single year. We know what works and what does not, and we can help you. It's in our interest, to Kelly's point earlier, to have strong proposals, because that means once the GA hits, we're excited to come here for the symposium, not just for Division G days, which clearly are the best part of the program, clear, but might not be the only part of the program that we are interested in.
Anyway, if you want any help about preparing your symposium before submissions, just please email me and we can do Zoom together. We can Zoom and we can discuss how we can manage your IAU symposium. Anyway, I'm really very open and flexible to any suggestion and any help that you can need. We can Zoom also, and there is no.
Very well. Thank you very much.
Thank you very much for your support and your trust. Thank you again, and I am sure I am really looking forward to working with you. I'm sure that we will achieve even more success for our Division G. Thank you very much.